They said it's going to come up. Hello. Oh. Good morning, everyone. Welcome to the first talk session this morning on separation logic, and our first talk will be given by Paolo.
Thank you very much for this introduction. Can everybody hear me? No. Should I wait for the mic to work? Is it working now? Can you hear me?
Working, but it's just very low.
Okay, can you somehow increase the volume of the mic? Can you hear me now? Better?
Can you get Derek's mic?
Sorry?
Derek's microphone?
Yeah, we just use this.
So, okay, I will remove this one then.
I think so. Is that okay?
Yep. So you can hear me now?
Yes.
Okay, thank you very much. Thank you very much for the introduction. This is joint work with Sinka von Colin, Ines Wright, and Robert Krebers. And I would like to start by saying what's the goal of this work. And in simple words, is to design a relational separation logic for effect handlers. And I imagine that when reading this goal, two questions come to mind. What is a relational separation logic, and why design one for effect handlers? So a relational separation logic, like any program logic, is the given of two things: an assertion language to specify programs, and a set of proof rules to verify programs compositionally. And the key feature of relational separation logic is the ability to reason about to compare the behaviors of two programs. And specifically, in relational separation logic, we can assert that the program on the right-hand side, on the specification side, is a correct abstraction of the program on the left-hand side, on the implementation side. And more formally, what this means is that every terminating behavior of the program on the implementation side is a terminating behavior of the program on the right-hand side. If it terminates with a value, the program on the specification side terminates with a value, and they're related by, these values are related by the postcondition. Now, why design a relational separation logic? Well, there are many interesting applications of relational separation logic, and here I'm listing only three. The first one is to verify programs and to reason about programs using simpler implementations as specifications. A second application is on compiler optimizations, and namely to show that a compiler optimization is correct by showing that the optimized program does not introduce behaviors, to use the source program as a specification of the optimized program. And a third application is to show both soundness and abstraction properties of type systems. Now, to show why relational separation logic is relevant for effect handlers, I'm going to focus on this application, on program verification and program reasoning. And I would like to discuss an example of effect handlers, and namely the fork effect, an implementation of the fork effect. And what we can think about this program is that it's implementing a scheduler for multiple currently executing tasks. All these tasks are suspended and stored in a queue, with the exception of one whose execution is monitored by a handler. When this running task performs a fork effect, the handler takes the continuation, which is a representation of the suspended task, and inserts this task in the queue, the continuation in the queue, and immediately starts running this new task. At the end of running this task, the handler will check for continuations in the queue, and if there's any, it will resume the continuation. So in my opinion, this is a very elegant implementation, also very concise, but it's also very hard to reason about because it uses advanced programming features, such as dynamically allocated mutable state and first-class continuations. So with relational separation logic, we can, in fact, abstract this whole program into one single line, where this fork functionality is simply given by a native fork instruction. And this statement also helps us to understand a fork effect as actually a native fork instruction. But it also reveals some problems, some difficulties in formalizing this statement, because here we are reasoning about a fork effect in isolation of its handler. And the issue is that an effect only has meaning under a handler. Its meaning depends on a handler. And this issue is going to come up in 3 challenges to design a relation separation logic for handlers. The first one is into how to specify programs, because if we look at the standard refinement relation in relational separation logic, it does not talk about effects. It only talks about terminating behaviors with values. So implicitly, there's the assumption that when we use this refinement relation, there are no effects on the implementation side. A second challenge is how to allow composition reasoning about handlers and handlers. So we would like to decompose the verification of a program with a handler into the verification of the handler and the verification of the program that performs effects. And to illustrate, if we want to verify the program I just showed, the statement, the relational statement I just showed before, at some point we would have to reason about the composition of a handler and the handlee. And at this point, we would like to split the proof into a handlee part and a handler part. And we can see here that, again, we come up with this problem of having to reason about a program that performs effects in isolation of a handler. And more generally, we would also like to the logic to enjoy some context-local reasoning principles, such as the reasoning principle allowed by the bind rule in standard relational separation logic, which allows us to, when verifying a pair of programs under a pair of contexts, to focus the verification into this pair of programs. And the question is, can we allow a similar rule in the presence of effects? So the key idea of our work is to come up with a new notion of refinement in the logic. And our idea is to parameterize refinement relation with a theory, which can be seen as an axiomatization of the relations that should hold. And this resulting logic, it's called base, and it's built on top of iris. So the way we formalize a theory in iris is by means of this function that takes as input a possible refinement between 2 expressions and a postcondition, and returns what is the condition for this refinement to hold. And what I would like to stress here as well is that nothing mandates that this theory talk about effects. Actually, these are arbitrary expressions. And this is important to give the logic the flexibility to allow us to relate effects with programs that are not effects. To give some examples, to make this more concrete, the simplest example of a theory would be the empty theory, where to refinement, the condition for this refinement to hold is simply false, meaning that there are no possible admitted refinement by this theory. If we instantiate the empty theory with our parameterized refinement relation, we recover the usual refinement relation in relational separation logic. A slightly more involved example would be that for fork effects. And here the question is, what would be the condition for a fork effect to be related to a native fork instruction with a postcondition R? And the condition is actually a conjunction of 2 conditions. The first one saying that the tasks should be related, and the second one saying that the postcondition should hold for the result of these operations, which are both unit. And using this theory, we can formalize the intuition I gave in the beginning of the talk, that a fork effect refines a native fork instruction under the assumption that the forked tasks are in a relation as well. So now we're going to revisit the challenges I listed before, the 3 challenges I listed before, and see how this new idea of a refinement, parameterized refinement relation would help us to solve these challenges. And the first challenge was that given that the meaning of an effect depends on a handler, how can we give specifications to programs using how can we define a refinement relation that gives meaning to programs that perform effects. And here the idea is to rely on this technique from the literature called B-orthogonality, which essentially means that under the hood, we're always talking about some universally quantified context. So under the hood, the definition of a parameterized refinement relation will quantify over context and state that these pair of programs are in a relation using the standard refinement relation of separation logic under universally quantified pair of contexts. And to establish this refinement, we have the assumption that this pair of contexts they validate the relational theory. And what it means to validate the relational theory, it means that if we plug related values to these contexts, we obtain related programs, and if we plug related expressions, we obtain also related expressions admitted by the theory, we also obtain related programs. So the way we solved the second challenge, which was the compositional reasoning for Handler and Handley, is by means of this exhaustion rule, which for the verification of a pair of programs under a pair of contexts, it splits the verification into the verification of the expressions themselves and a condition on the contexts. And what is important to note here is that when applying this rule, the user has to come up with a theory to carry on with the proof of the refinement between the expressions. And what the condition on the contexts means is that the context, again, validate this theory. And it's very similar, actually, to the definition of the refinement, with only the difference that here we also allow the statement for the refinement between the contexts. It also allows a theory for its F for itself. And what I would also like to notice again is that these contexts, nothing mandates in this rule that these contexts contain handlers. And again, this gives the flexibility in the logic that when applying this rule, there could be a handler on the left-hand side, but no handler on the right-hand side, and vice versa. So, what I would like to also highlight is that this rule kind of enforces the idea that the theory is an abstraction on the eyes of the program that performs the effects of the handler, and for the handler is an abstraction of the program that performs the effects. And finally, the logic also allows a principle for context local reasoning with the naturally extension where we annotate the refinement statements with a theory. And it contains, the only difference is that it also contains a condition that this theory be traversable. And one intuition is that it allows us to commute a theory with a pair of contexts. And another intuition is that a theory is traversable for a pair of contexts if it holds regardless of this pair of contexts. And that's what it allows for this rule to be sound, and to, when we focus on this pair of expressions, we can ignore this pair of contexts and still have this theory. So I'm not going to give the definition of what traversable is, but what I can say is that not all theories are traversable. But thankfully, the logic has a mechanism to make theories traversable by construction. So again, I'm not going to give the definition of what a context closure of a theory is, but I'm going to characterize it through two properties. The first property being that the context closure of a theory extends a theory, meaning that every refinement that's valid and that is admitted in the theory, original theory, is also admitted in the context closure. And a second property is that the traversable condition on a context-closed theory simplifies into a conjunction of syntactic conditions on the contexts. And what this syntactic condition means is that there are no handlers in these contexts for effects in this set, but there could be handlers for effects not in this set. And when we instantiate the bind rule with a context-closed theory, we obtain a version of the bind rule where we exchange the traversable condition for syntactic conditions on the contexts. Now we're going to revisit the example from the beginning of the talk and see what their key ideas to verify this example. So there are three key ideas. The first one is that we must come up with a theory to reason about these fork effects. And not surprisingly, the theory is going to be the one I showed before, the theory about fork effects. But we're also going to take the context closure of this theory. And with two sets, the set on the left-hand side is going to be the singleton set with fork effect, because it's the only effect in this program. And on the right-hand side is going to be the empty set, because this program doesn't have effect. And the second step is going to be to apply the exhaustion rule to decompose the proof between a proof of the handler and a proof of the handler. And what the handling part will look like will be this refinement. And in this refinement, we're going to use the bind rule to focus on these, on the perform effect, on the perform fork effect, and on the fork instructions, and then rely on the theory to prove to finish the proof on these specific atoms. And for the verification of the handler, it happens that we could not use the standard relational separation logic to reason about concurrency in this program for a very simple limitation that in most previous relational separation logics, we could not reason about the case in which the fork instruction in both of the programs do not match. And that's clearly the case in the program I just showed before, because there are no forks in the left-hand side. So we have to come up with three novel reasoning rules for concurrency, which are independent of effect handlers. And I'm not going to go super in detail into these rules, but I'm going to give you an idea of what their use looks like in the verification of the program I just showed. And to do that, I'm going to use this box where on the bottom we have the goal, the refinement we want to show, without the theory and without the postcondition, just to simplify. And on the top of this dashed line, we're going to have the goal. So the rule for R, we're going to need it to reason about the case in which the program on the left performs a fork effect, and the program on the right is about to call the native fork instruction. And what this rule is going to allow us to do, this is a case that previous relational logics wouldn't allow, because there's not necessarily a fork on the left. And what this rule will allow us to do is to introduce this resource called a thread pool resource, which tells us that on the right-hand side, there is a thread with identifier I that is executing the program, this task. Now expanding this, the handler branch, we're going to have two instructions, an update to the queue and the run. So in the proof, we're going to have an invariant for the queue, in which every continuation in the queue, for every continuation in the queue, there's going to be a thread on the right-hand side with which this continuation is in a relation. And so we're going to need a thread pool assertion for this thread on the right with which the continuation is in a relation. But this is not the thread on the right with which the continuation is in a relation. The thread on the right is actually this, the one on the right side of the judgment. So we need somehow to obtain the thread pool assertion for this program. And what this rule allows us to do is to exchange these thread pool assertions to obtain one describing the main thread on the right. And now we can update the queue, maintaining the invariant, and the rest of the proof just carries on with an inductive argument. And finally, we have to verify the return branch, and at this point, we're going to pop a continuation from the queue and reobtain a thread pool assertion for some thread on the right with which the continuation is in a relation. And what now this rule will allow us to do is to allow us to think of this program on the left-hand side as if it was being forked, and use the assertion that they are in a relation to finish the proof. So to conclude, in this talk, I showed you the importance of relational separation logic for program verification and program reasoning, specifically with the fork effect. And the main challenge coming from this issue that the meaning of an effect depends on a handler. And I show you the base logic, which is built on top of Iris, with the novel idea of refinement relation parameterized by a theory. I showed you that base allows compositional reasoning about handling and handling, and also context local reasoning. And I showed you that we introduced novel reasoning rules for concurrency that are independent of effect handlers. And in the paper, there is much more. Actually, what I showed is base, and implicitly, I was always talking about static effects, but there's also a logic, a whole other logic in the paper for dynamic effects built on top of base. There's also discussion about deep and shallow handlers, to which both these logics have support, and also one-shot and multi-shot continuations, again, to which both logics have support. And we also have many other interesting case studies, namely some refinements between asynchronous programming libraries and a handler correctness criteria in Blaze for algebraic effects for non-determinism. Thank you very much, and I'm glad to take questions.
So there's an interesting difference between the theories you're presenting here and the notion of protocol you've used in previous work on program logics for effect handlers.
Notion of what? Notion of what, sorry?
Of protocols.
There is,
And specifically, I wanted to ask that they're now parameterized over expressions instead of values.
Yeah, exactly, yeah.
And I wanted to ask whether that could also give interesting reasoning principles for unary logics as well.
That's a good question. So, yeah, so two obvious differences. One you mentioned, these are expressions. So in protocols from the Hazel logic, they were always values, meaning that we always have to reason about specific effect instructions. And another difference, obvious difference, is that this is binary and not unary. And the question is whether this gives you some intuitions for unary case. And to start with the definition of the refinement relation, we could think about a definition of a unary logic where we don't, so in the Hazel logic, we had a custom-made weakest precondition. So in this logic, we can always rely on the traditional refinement relation of the logic. So that would be one idea to improve on the unary case. And another idea, I think we could also have a more flexible bind rule, which is not really related here to unary or binary case. It's kind of independent, but which actually relies on these being expressions rather than values.
Okay, thank you.
No problem.
Sorry, could you? One more quick question for Ahmed.
Hi, thanks for the talk. Can you go to the next slide, actually? Slide 15, I think.
Sorry?
The next slide, slide 15. Yes, so you have this, this context closure operator, and now you have this traversable equivalent to this syntactic property.
Yeah.
Is it equivalence or is it one direction?
It's equivalent.
It's equivalent.
In this case, it's equivalent.
So, but your traversal property, is that a syntactic property or a semantic property?
It's a semantic property.
Okay.
Yeah,
So
it's defined semantically, but
defined
in this
semantically-
case, in the specific case of a context closure, these are equal.
Okay. Yes. Thanks.
Take further questions offline and thank Paulo. Our next speaker is Xinghin Ho, who will tell us about Bayesian separation logic once his slides come up. Do you want to try speaking? See if it... Oh, it's not. Hold on one second. Can you try, see if his body mic works? Yeah?
Hello. Does it work?
No.
Okay.
Oh, it does?
Does it?
Can people hear him? Speak, say something.
Hello.
No.
Okay, I'll just use this one. Yeah.
We'll just use the handheld mic. Yeah, I think the handheld is easier.
Hi, I'm Xing Hin, and today I'm going to be talking about our work on what's called Bayesian separation logic, which gives an axiomatic semantics to what's called probabilistic programming. And this is joint work with my supervisors, Azelia Rad and Nick Wu. So to begin, let me first talk about, well, our goal of the project, and it's to reason about probabilistic programming using what's called probabilistic separation logic. So what's probabilistic programming? Let me illustrate this by with an example. So let's say, well, now, for example, if I found a coin on the floor, and I want to know, well, if it's a fair coin or not. So what can I do? Well, I can flip the coin and get back a bunch of samples, let's say C1 to Cn. So what we can do is to actually estimate, well, using what's called the Bernoulli distribution of x, which it returns 1, so that's heads, with probability x, and 0 with probability 1 minus x. So our goal is, therefore, to estimate x between 0 and 1. So if x is 0.5, for example, then it must be a fair coin because it returns 0 and head and tails with equal probability. If it's 0.9, then it's a biased coin towards heads because, well, it returns heads with 90% probability. And if it's 0.1, then it's a biased coin towards tails. So the key feature of probabilistic programming is what's called Bayesian conditioning. So suppose now I have a flat prior belief about my coin. So that's saying, well, I don't have much assumptions. X could be 0.75, or it could be 1. I have no prior belief, a flat prior belief about on this. Now, if I flip a coin, let's say if I get back heads, and I'll call the coin C1. So this changes my belief slightly because, well, now I have one sample, but I'm more inclined to believe that, well, it's more likely to return heads. So mathematically speaking, this basically updates my belief to what's called the beta 2-1 distribution, which basically says it's more likely to return heads. So if I do the same thing again, I flip a coin again, I get back tails this time, and I call it C2. So now my belief is shifted again to what's called the beta 2-2 distribution, which is to say that, well, it returns, well, I kind of think that's fair, but I'm not very certain about it. So because, well, out of all the samples I have, which, well, it's 2 samples really, one of them is head and one of them is tails. So probabilistic programming languages is basically a programming paradigm that allows us to express these models as programs. So given this experiment that I have, I can actually write this very simple program that basically runs and gives me back the beta 2-2 distribution. So the first line of the program says, I sample from my prior belief, which follows a uniform distribution on the interval. And the second line basically flips the coin according to the Bernoulli distribution that says, well, I return 1 heads with probability x, and, well, tails with probability 1 minus x. Now, if I condition on C1 to be 1, so that's with the observed construct, well, something actually changes. So before executing this line, I can sort of think of, well, the distribution of x being the unif 0 and 1 distribution. But after this, it actually changes my belief to what's called the beta 2-1 distribution because, well, I'm now slightly more inclined to believe that, well, it returns heads more often. So, well, at the end of this program, I actually get back the beta 2-2 distribution. So now, well, given this program, I want to prove some properties about this. Well, can we, well, reason about them logically? So for example, can I prove that expected value, so that's the average, is approximately 1/2? So, so this has a well-defined denotational semantics using what's called S-finite kernels. And we can always integrate this expression and get back 1/2. But can we actually do a line-by-line reasoning and get back some sort of Hoare triple that reasons about these programs and have a more high-level description of them? So this is basically the second part of the talk, which is about, well, reasoning about these programs using probabilistic separation logic. So what's probabilistic separation logic? So we know that, well, separation logic is basically a logic of computational resources, and probabilistic separation logic is the logic of random resources. So the syntax of PSLs is as follows. So we have on the first line, we have the standard separation, first order logic stuff that says we have conjunction, disjunction, some quantifiers. And for the second line, we have the probabilistic stuff, which says, well, the first one says that X is distributed according to a distribution P. And the second one says the expected value of X is some expression E. And the third and fourth one, well, are the separating conjunction and, well, the magic wand, which is the right adjoint. So P star Q in the case of PSL basically means that, well, P holds, Q holds, and also things in P and Q are probabilistically independent. So let me give an example. So let's say I have this proposition that says X is distributed according to a fair coin, star Y is distributed according to a fair coin. So what this means is that, well, this needs to be supported by something that basically flips 2 coins, because I can't say, for example, I flip a coin and call it X and negate the result and call it Y, because this will not be probabilistically independent. Because if I know something about X, if I know that X is 0, then Y must be 1 in this case. So our work is called Bayesian separation logic, BASL. So it's a new model of probabilistic separation logic such that it's the first logic to support the observe, or more generally, the scoring construct in PPLs. So let's look at this example. So if I flip a coin and observe that the coin is 0, then, well, from a true precondition, I can actually prove that, well, the post-condition is that, well, the coin returns the Dirac 0 distribution, which means that it returns 0 all the time. And the second feature is actually dependencies during sampling. So if I have, look at this program, if I sample X and it follows a uniform 0 and 1 distribution, if I now sample Bernoulli of X according to C, so roughly speaking, we know that C is basically a fair coin in this case, but we can also talk about something else. So from a true precondition, we can say that, well, C has a conditional distribution that says if we condition on X being a certain value, then C will have Bernoulli of that value. So I'll illustrate the proof of these two features. So suppose we start from a true precondition, and we now sample, well, we flip a fair coin. Then there's this sampling rule, which is quite standard in probabilistic separation logic, that says from a true precondition, if I sample P, a distribution P, then the output variable X has distribution P as well. So this would mean that, well, we have a post-condition that says coin is distributed according to Bernoulli of 1/2. And now, well, if we observe that the coin is 0, then what we would get is, well, using our new observation axiom that says, given a precondition that says x is distributed according to pi, and if we observe p of x to be true, so p of x is some random expression, for example, then x has distribution L of p times pi, which in this case basically amounts to coin having the Dirac zero distribution, which returns 0 all the time. So this kind of intuitively makes sense because, well, if we condition that where the coin is 0, then it must return 0 all the time. And the second feature is the conditional sampling rule that says, let's say if we now sample x and it follows a uniform 0 and 1 distribution, applying the sampling rule again, we get back this that says x follows the uniform distribution. If we now say that, well, we sample C according to Bernoulli of X, then so this one's slightly more intricate. This is a slightly more intricate rule that says it's a conditional sampling rule that says given a precondition X is distributed according to P. Now, if we sample little p according to X, then we get back this a variable y such that, well, there's this new construct. Well, this is introduced in the lilac separation logic, and it's called the conditioning modality, basically saying that, well, it says that, well, for every possible value of x, for almost all values of x, the little x, and we call it little x, and y has a conditional distribution that says p of little x is true, which in this case basically amounts to saying that for almost every possible value of my random variable x drawn from the uniform distribution, C has distribution Bernoulli of little x. So recall that we're trying to prove that the expected value of this program is 1/2. So now I'm going to show you how to do that. So we start from a true precondition, and we sample x. And if we now apply the sampling rule, then we get back x is univ of 0 and 1, as we've seen before. Now, if we sample C1 again, then by applying the conditional sampling rule, we get back a conditional distribution of C1 that says C1 is distributed according to Bern of x for almost every possible value of x. Now, if we observe that C1 is 1, we also have the conditional observation axiom that basically says that if I can basically do the observation, but conditionally on something, because I've conditioned that C1 is 1, then my post-condition says, well, for every possible value of x, C1 has distribution Dirac of 1 because we assumed that it's 1. So this is the tricky part of the proof. So I'm saying that, well, given this precondition, this conditional precondition, I can turn it into what's called the beta to 1 distribution, and with this theorem called the internal base theorem, which is the main theorem of our paper. I'll explain this later, but so if we continue with the proof and say that, well, we sample Bernoulli of x from C2, and now, well, by applying the conditional sampling rule again, we get back C2 has distribution Bern of x. Well, we now observe that C2 is 0, and we get back, using the conditional observation rule again, that C2 has distribution Dirac of 0 now. And we now apply the internal base theorem again, and get back x is distributed according to beta 2, if we now return x, because we know that, well, beta 2 is basically a primitive distribution that has expected value, or an average 1/2, we can show that, well, by the rule of consequence, we can show that the expected value, or average, is 1/2. So this completes the proof. So these are our proof rules. So I've explained most of them, and I haven't explained the frame rule and the return rule, but these are slightly standard things in separation logic. So another example I want to show is conditional dependency. So let's say if we now have 2 coins, let's call it X and Y. Then I get back a post condition that says X and Y have the distribution of coin, and they're independent using the frame rule. If I now say that, well, Z is X or Y, and I now condition that Z is 1, so what would happen now? So X and Y would be, well, no longer independent conditioning on this because, for example, if I know that Z is 1, and I know that X is 0, then, well, because Z is defined to be X or Y, then, well, Y must be 1 as well. So knowing something about Z and X gives me extra information about Y, so that's why it's no longer independent. And if we return X and Y, we can actually prove that the correlation of X and Y is actually negative. So what this means is that, well, if X increases, Y is likely to decrease, and if X decreases, Y is likely to increase. We have other features as well, such as loops, and we use it to basically prove things such as a clustering algorithm in Bayesian inference. And if you're interested in this, the proof is slightly long, but if you're interested in this, you can read our paper. So for the final part of the talk, I want to talk about the semantics of probabilistic separation logic. So the semantics is basically a stream of random numbers. So I spoke about how separation logic is basically a logic of resources, and probabilistic separation logic is a logic of random resources. So in the lilac separation logic, they basically define it as a stream of random numbers, which is defined using what's called a probability space over the unit interval to the power of n, which basically amounts to a stream of random numbers. And we extend this model to what's called a countably generated sigma finite measure space. So sigma finite measure space basically means that, well, we can have a normalized distribution as well, and we can talk about Bayesian stuff. And so countably generated in this case means that it's well behaved enough such that it forms a certain model. It forms what's called a partial commutative monoid, which gives semantics to separation logic. So our main theorem is what's called the internal base theorem. So recall that I said, if I have these two statements, if I have a prior belief that, well, the coin is, well, I have no prior belief, the belief is flat. And if I now observe that I get back heads, then this is the same as saying, well, I have a beta 2-1 distribution. So the entailment, by implication, that goes from, well, the first half of it to the second side, and to the second side to the first side, the left-hand side of the statement. So this is justified, semantically justified, using this theorem, which basically says that we can do that. And the proof of the theorem is slightly intricate, and it relies on two things. The first thing is called the sigma finite disintegration theorem, and the second thing is called the existence of Barrow extensions. So what this means is that, well, if we have a stream of unnormalized random numbers, we can always have a random variable and take the conditional on it, which even when, for example, the random variable has measure 0 or probability 0, this would still work, and this is justified using these two theorems. So to conclude, I've introduced Basel, which is the first separation logic to support two things. The first thing is the observe and scoring construct, and the second thing is dependencies during sampling. And if you're interested, please read our paper, which also talks about, well, how the sigma finite model of probabilistic separation logic is defined, and also how it relates to existing denotational semantics. So that's the category of S-finite kernels. As for future work, we're quite interested in how can we define separation logic from a higher order continuous probabilistic programming language. as well as, for example, lean formalization, and how can we recognize our result in a proof assistant. So that's all. Thank you very much.
Thank you for the talk. I have a small question. When you mentioned that X is like X arrow, X capital, and you said it's for almost any value, you qualified several times. Can you explain why it's almost any value, not any value?
If I go back to the slide, when I said that X has so in this case, it basically means that for every possible value, for almost every possible value, so that means because I have a distribution in mind, so that's a uniform distribution. So for almost all values, simply means that, well, the probability of not drawing that of things outside of that value is 0. So that basically means you can, for a first approximation, think of it as like for everything between 0 and 1.
Thank you for the talk. I was a bit confused about the beta Bernoulli example with a coin, because it seemed like the observed statement would also normalize the distribution. Mm-hmm. Is that the case or not?
So not really. So there's an existing denotational semantics, which basically allows you to express them as unnormalized measures, and that's needed because of a construct called score, which I haven't explained, which basically allows you to express some weird measures, such as the Lebesgue measure, which is not normalizable in the language itself.
So in the beta coin example, there should have been a factor before the beta distribution?
Say again, sorry.
So in the beta coin example, there should have been a factor in front of the beta distribution? Because it's not...
Yes, so I've kind of omitted this detail, but then we are keeping track of the normalizing constant in our logic as well.
Sense.
Yeah.
Thanks.
Further questions? All right, let's thank the speaker. Our next speaker is Arthur, who will tell us about Cryptus. I think it might be better in the... because it was a bit too long. Hello? Let me... Hello.
Okay, good. So like many stories, our story today starts with two characters, Alice and Bob, except that because we're in France, we should actually call Bobby Bobby. We're going to stick to Bob anyway. In any case, Alice and Bob own nodes in a network, and Bob has a server that stores some integer that Alice wants to know. So Alice sends a request to Bob asking for this value, and then Bob replies with the answer. Now, if this is taking place over a private network, where these are the only two nodes, then Alice can be fairly confident that the answer she got is accurate, that it reflects the integer that is stored in Bob's server. But now, let's assume it's more a slightly more interesting scenario, where this is taking place not over a private network, but over a public network. Now, when we send a message, this message is not going to be relayed directly to the person we want to talk to. It's going to be relayed over a series of intermediate nodes that could be, for instance, controlled by attackers. So the attacker might be able to intercept Bob's message and replace it with some other value, tricking Alice into believing that something incorrect is true. So what can Alice do to prevent this kind of situation? Well, one solution is to use encryption. So now, instead of replying to Alice with a plain text message, Bob is going to encrypt his response using a symmetric key that is known only to himself and to Alice. Now, when Alice reads this message, if she managed to decrypt it, she can know that the answer is accurate because there's no one else that could have produced this message. If an attacker tries to trick her into believing that an incorrect value is the correct one, he will not be able to do that. Now, if we were to consider a slightly more realistic setting, where we might deploy something like this, we would see that it would be more complex along many axes. For the first thing, it will generally not be the case that Alice can start talking to Bob right away. She might have to initiate some kind of authentication protocol to prove her identity to Bob, and also to exchange some session key with him so that she can use to encrypt the communication. When the communication starts, what they're going to exchange is typically not going to be a simple call and response pattern. We're going to have several messages flowing back and forth. And also, the logic of the actors themselves internally might be more complicated. For instance, Bob might not be a monolithic server, but it might be some kind of distributed system that it's running its own protocol. And we'd like to make sure that despite all of this complexity, everything behaves correctly from Alice's point of view, even in the presence of evil attackers. So how could we do this? Well, because this is the separation logic session, I guess it won't come as a surprise that we might attempt some kind of formal verification. And in particular, we might attempt to reason compositionally, right? So maybe we could say, okay, let's formally verify the protocol that is allowing the agents to communicate, and let's formally verify whatever application logic is sitting on top of this protocol. And then we can just put the two together by composition, and everything works. That would be great, except that if you were to try to do this in practice, you would face several obstacles. One obstacle is that the tools that he would use to verify each piece of the puzzle don't really talk to each other. To verify the application logic, we might use some kind of general purpose proof assistant or verification programming language. But to verify the protocol bits, you would typically resort to domain-specific tools. These tools are great for verifying correctness properties of cryptographic protocols, but they don't really talk to these general purpose tools. So we wouldn't be able to compose the correctness results. Even if we were able to compose these results, we would face a different obstacle, which is that the notion of correctness that we use for cryptographic protocols was not designed with reuse in mind. So for a cryptographic protocol, typically we would like to prove that when agents authenticate with each other, they can prove their identities to each other so they know who they're talking to. And we might also like to prove that the session keys that they exchange are secret. On the application side, we might like to prove an application level property, such as showing that every read that we get back from the database reports the correct value. And we might be able to prove this using some kind of reliable communication abstraction, but it's not clear how we might substantiate that this reliable communication abstraction is correct based on just the properties that I enumerated there for the cryptographic protocol. And this leads me to the work that I'm presenting today on this Cryptis logic. Cryptis is an integrated logic for proving properties of systems that include cryptographic components. And it's built on two core ideas. The first idea, which intersects with other related work in this area, is that we should be able to enable the reuse of protocol proofs by leveraging advanced features of separation logic in the so-called symbolic model of cryptography. So as you might be aware, separation logic is nice because it's an expressive program logic that enables compositionality by focusing on resources and coordination and independence of resources. Symbolic cryptography, on the other hand, which I guess less of you are familiar with, is a paradigm for reasoning about cryptographic code in which we assume that agents can communicate over a network, but that the network is controlled by attackers. These attackers are capable of manipulating messages arbitrarily, but in doing so, they're bound by an assumption of perfect cryptography. So this means that when I receive a message and I try to decrypt the message, the decryption will only succeed if I have the key that matches the encrypted message. Moreover, it should be impossible for me to simply guess this key out of thin air. I can only generate a key myself from scratch, or I can get an existing key from somebody else. Once I have a logic that has these two parts, symbolic cryptography and separation logic, I can use these features to verify the cryptographic protocol, verify the application logic on top of it, and put the two together. But this only works, as I was mentioning earlier, if we have a notion of correctness for cryptographic protocols that allows this kind of reuse. This is where the second idea comes into play. We take inspiration from prior work on the verification of distributed systems, and we argue that the specifications for cryptographic protocols should really allow agents to coordinate on the use of separation logic resources. And of course, because we would like this whole thing to be built on a minimal TCB, Cryptus is designed as a library on top of the rock-proof assistance and of the iris separation logic. So in the remainder of the talk, I'd like to give you a brief tour of Cryptus and show what kind of examples we can verify with it. I'm going to work with the hello world of protocol verification, the Needham-Schroeder-Lowe protocol. In this protocol, Alice wants to authenticate with the server Bob, so what she does is that she sends a message to Bob encrypted under Bob's public key. And this message contains a fresh nonce that Alice just generated along with her public key, which serves as her identity. Assuming that Bob wants to accept the connection, he's going to generate a nonce of his own and reply it back to Alice with a similar message. And then finally, Alice confirms the end of the handshake by sending Bob's nonce back to him. We'd like to prove the following spec for the function that Alice runs. What does the spec say? Well, we start out by assuming that the public keys of the agents are indeed public. In Cryptus, we have this special public assertion, which describes things that can be sent over the network. And because they can be sent over the network, they can be inspected by attackers and manipulated by attackers. We also assume that the private keys of the agents are kept secret. For those of you who are familiar with Iris, you will notice that here I have guarded these negations with the persistence modality, which means that negation behaves as a logical assertion and not as a separation logic resource. In any case, assuming that the initiator code terminates, we're going to get two nonces back, an A and an B, that are guaranteed to be secret, and we're also going to get some application level property phi that holds of the identities of the agents and of the nonces that they just exchanged. What's novel here is that this assertion is not a traditional logic assertion. This can contain arbitrary separation logic resources that tie together the agents and the session that they have just initiated. In the paper, you also see a more general situation where we're talking to an agent who's not necessarily assumed to be honest. So let's see how this proof goes. Here I have the code that I'm verifying, the current proof state, and the end goal that we're trying to achieve. To do this proof, we're going to rely on Cryptus rules that expose the reasoning principles behind symbolic cryptography, but allow us to use separation logic resources in them. So let's see how that works. We start by allocating a new nonce for Alice. In Cryptus, we reason about this using the following rule. This rule says that the nonce that we generated is guaranteed to be secret. So we have the secrecy resource that describes terms that are not yet known to the attacker. We can choose if and when it will be revealed to the attacker. We also obtain a freshness resource describing terms that have not been used yet, that have been just generated. For the NSL protocol, the usage that we want to make of this nonce is rather simple. We always want the nonce to be secret, so we use this little proof rule that allows us to consume the secrecy resource to create a nonce that is permanently secret. In the paper, you will see usage of the secrecy resource that's a little bit more interesting and that allows us to describe dynamic compromise of cryptographic material. The next thing that we do is to encrypt the first message. And to do that, we use the following rule. This rule says that encrypting a term is safe provided that two things hold. Number one, the private key that matches the public key that we're using ought to be secret. And the reason for that is that we don't want the attacker to be able to read the contents of the message, because if the attacker were able to read the contents of the message, we would also need to show that the contents are public. We also have to prove that some application-specific encryption predicate holds of the contents of the message. For the NSL protocol, we're going to choose this predicate to simply say, for the first message, that the nonce that Alice is sending is public, which it is, because we have generated it this way. Once encryption returns, it is going to return a public term, which is good because we want to send that over the network, and we use this proof rule that says that anything public can be sent over the network. Then Alice waits for a response, which is guaranteed to be public because it came from the network, could have originated from an attacker, and then she's going to try to decrypt this message. To decrypt a message, we use the following rule, which says that anything public can be decrypted, and if decryption succeeds, we're going to be in one of the following two cases. One possibility is that the contents of the message are public. So this represents a situation where the message that we got was produced by an attacker. For the NSL protocol, however, we're checking that the message that we get back contains the nonce that we sent originally, which is good because we generated this nonce to be secret, which means that we can rule out this possibility. Which leaves us with the second case that says that the encryption predicate that we chose for the second message holds. For the NSL protocol, we want to use the following predicate, which guarantees that number one, the nonce that Bob generated is also secret, but number two, that some escrow assertion holds. So an escrow is a design pattern in separation logic that allows us to use a persistent assertion to trade in one ephemeral resource for another. And here we're making crucial use of the advanced, rich assertion logic that Crypt is built on, that allows us to write these escrow assertions in the first place. In any case, once we have this escrow, we can trade in the freshness resource that we got for the nonce and obtain whatever application level resource we care about. So why is this useful? Let's consider how we might use this protocol at a high level. Here we have a simple application where we have some authentication step composed with a reliable communication abstraction and whatever application logic we care about. We might implement our authenticated key exchange using a protocol like the one I just showed you, where we use the cryptographic material that we exchanged to derive some kind of symmetric encryption key. Above that, we're going to have a reliable communication abstraction that is implemented using symmetric encryption, where we use sequence numbers attached to every message to guarantee that messages arrive in order and that they're also not duplicated. Logically, what that means, again, taking inspiration from this prior work, is that every message that we send and receive comes with an associated resource that is determined by whatever application we're verifying. Here we're using this so-called session escrow pattern that comes from previous work, which requires us, crucially, to mirror these sequence numbers that are stored in concrete program state in ghost state. And for this, we make crucial use of the fact that when we launch this handshake, we can exchange separation logic resources and coordinate their use. right? In particular, when Bob sends back some resource to Alice, he can allocate the initial Go state used to store these sequence numbers, which is going to guide the use of the escrow pattern on the app communication layer. Once you have established this abstraction, you can use it to verify whatever application level property you might care about. For instance, if you're verifying a key value database, you might be able to show that you can manipulate the database as if it were local storage by using some kind of points to resource. And with that, I think I am at the end of the talk, actually. So just to wrap up, there are two key takeaways that I would like you to take home. One is that protocol specifications should really be designed with reuse in mind. A protocol is not something that you verify for its own sake. It's something that should be reused in a larger system, and the specification should reflect that. And crucially, separation logic is a key ingredient for making this type of integration possible. You will see much more in the paper. We have more complicated protocols that we have verified, notably protocols built on Diffie-Hellman key exchange, which allow you to prove advanced security properties. In particular, they allow us to analyze non-trivial compromise scenarios where you have agents that can have some of their keys compromise and still get some interesting security guarantees of forward secrecy that hold in that setting. We also discuss how we use this methodology to do the end-to-end verification of a key value store. And of course, there's a bunch of future work that we'd like to do. We're working right now on integrating this with session types and La Actress, but also doing relational versions of Cryptus to prove even stronger the secrecy properties. And we'd also like to generate models, Cryptus models from running implementations. And that brings me to the end of the talk. Thank you.
Thank you for the very nice talk. So I am not an expert in verifying crypto protocols, but from what I know, there was a work done, and I think you quoted it by Leonard Arkind and his co-authors, yes, who took models in Tamarin and proved the refinement of those protocols at the level of the implementation in Go using Viper. So could you highlight the conceptual differences between what you have done and what they have done?
Yeah, so the main difference between our work and theirs is that they are concerned with this problem of how do you take an actual protocol implementation and verify it according to these protocol specifications that people have cared about. The main difference is that the specifications that they use are not built with reuse in mind. So they really didn't ask themselves the question of, well, now that we have these specifications, how do you use this for something else, like a distributed system or a database or something like that?
I'm very sorry, just to follow up, and which examples in your case demonstrate this reusability? I can look it up in the paper, but...
Yeah, so essentially in this diagram, you could consider that they stop here and that they have a specification that works for just this piece. The logic that we use and the case studies that we consider cover this entire thing.
Thank you.
Oh, thanks for the talk. So in symbolic crypto, the primitives are considered usually perfect, right? But you also have tools in Iris like Clutch where you can basically verify the primitives. Would it make sense to create some sort of connection between Clutch and Cryptis so that one can verify the primitives and the protocol within one framework?
Yes, so it's a pretty open problem in crypto to draw a strong connection between the symbolic and the more concrete computational model. And the main issue is that in the symbolic model, the specs are very clean, they're perfect, right? Whereas when you move to the computational world, everything is approximate and up to, I don't know, some probability of error at the very least. So yeah, I think we have to solve some more fundamental problems in crypto before we can start incorporating that.
much. I was just curious about, can you say a little bit about the adequacy theorems that you prove? I mean, what kind of statements can you get externally in terms of the secrecy? I was wondering a bit about that.
All right. So the adequacy theorem says a couple of things. First of all, it says that it assumes that you prove a spec for a program in a context where you have a resource that allows you to define what application level encryption predicates you want to use when verifying a program. So you're going to use this resource to set up your verification. And after you do this, you get the usual iris property that says that, well, if you have a pure postcondition, the pure postcondition must hold of the result. So by itself, this doesn't tell you anything about secrecy. The way you reason about secrecy is to say, well, let's set up a little game around my protocol where I have an experiment where the honest agents are interacting with an attacker. So the attacker should be able to, for instance, output the value of a session key on a public channel. And you can show by the rules of cryptos plus adequacy that it will be impossible for the attacker to output this value, for instance.
Yeah, so I wanted to also ask about this perfect secrecy perfect crypto assumption, and whether you could still analyze it with respect to a sort of perfect randomness assumption if you were to somehow incorporate like the number of times in which you use this assumption of perfect crypto, so that you know that you aren't in a loop that's going to try, every possible option or something like this.
Right. I think that this is something that people have looked at to some extent. It's just not clear how it generalizes to all possible symbolic crypto primitives that you might want.
Thank you for the great talk. I'm just curious if you could say a few words about the underlying resource monoid that drives the separated conjunction. Like, what is it that you track in the resource?
Right, so there's two main components. One component we inherit from base iris, and this is the part that we use to reason about freshness. So under the hood, all these nonces and cryptographic terms are implemented using heap locations in heap lang. So we use that to reason about freshness. But then on top of that, we have some higher order ghost state resources that we use to track these encryption predicates associated with terms.
Okay, thank you.
I'll ask. Quick question. Following on Lars's question about adequacy, with these protocols, often you need to make some don't you need to make some assumptions at the beginning about like keys that are known for the different parties? And if so, how do you discharge those assumptions?
Yes, absolutely. So So one thing is the verification of the protocol itself, right? So there you start with some assumptions. The way you come up with a ground truth statement to reason about the security of this thing is by wrapping it in the security game. And the game is responsible for initializing the state. So the game is going to allocate the initial keys. It's going to disclose whatever it needs to disclose to the attacker. It's going to compromise whatever it needs to compromise.
So that's sort of part of the operational semantics.
That's right.
Okay, in the interest of time, I think we'll stop there and thank Arthur. All right, for our last talk of the session, Netta will tell us about separating the wheat from the chaff.
Does it work?
Yeah, they're working on it. Takes them a minute.
Okay.
Thanks. I'm Neta. Thank you for staying for my talk. So this is joint work with Aditya Murali and Sharon Sham, my advisor. This is separating the wheat from the chaff, understanding incompleteness of proof mechanisms for separation logic with inductive definitions. Okay, so first, what is separation logic? And this is kind of a funny question to ask after this entire session, but maybe this is more for me to orient my first order mind into separation logic. So separation logic is a logic for reasoning about shared resources and specifically locations in the heap, in heap manipulating programs. So we have some heap with two parts. One part of the heap, there's this formula psi that captures some property over it, and phi, and we can combine disjoint parts of the heap with the separating conjunction, psi star phi. And in the way I think about it in this talk, so we have entailments that capture verification conditions. So we have this some verification condition that is captured by this entailment psi star phi entails alpha, and we ask, does every store and heap that satisfy psi star phi also satisfy alpha? And crucially, I'm going to talk about separation logic without magic wand. Okay. More specifically, separation logic with inductive definitions, SLID. So we enrich our language with inductively defined relations in the heap. So for example, we can have this inductively defined list predicate. So we can have a singleton list, which is just a nil, or we can extend some list from the left. So in this picture, we have the heap where D points to C, points to B, points to A, points to nil, and every memory location in the heap satisfies this list of X predicate. Okay, and SLID is a very expressive logic. We can do a lot with it, but it is incomplete. There's no complete proof mechanisms for it, and it means that when we try to prove things, we might fail, and we won't know exactly why we fail. But it does have some sound proof mechanisms. And one prominent one is fold and fold reasoning, where we reason by either taking an inductively defined predicate and unfolding it to its definition, or we take formulas that satisfy the definition of a predicate and fold them into applications of the predicate. And usually we expand and extend fold and fold with more reasoning, like inductive lemmas and stuff like that, but also by itself it can prove some entailments, but it fails to prove other entailments. And in this work we try to understand why and when that happens. So what is exactly the power of reasoning we can do with fold and fold. So let's begin with a concrete running example. We have this inductively defined acyclic list segment, L-seg xy. So L-seg xy holds when we have a singleton segment, x equals to y, or we have some segment L-seg uy, and x points to u, and so we extend the segment from the left. And we ensure that x is different than y to have an acyclic segment. And this inductive definition gives us the following proof rules with fold and fold. So for fold, we have these two rules. So t equals 1, t1 equals t2. We can deduce L-seg t1, t2. And for the other part, if t1 is distinct from t2 and points to some t3, where L-seg t3, t2, we can also deduce t1, t2. And conversely, if we know L-seg t1, t2, we can deduce the definition of the inductive predicate. Okay? And when we use this unfold rule, we introduce some fresh constant that replaces the existential quantifier from the definition. So let's take a look at two valid entailments that we would like to prove with fold and fold. So the first entailment, which is shown in green, which is good, says that A is distinct than C, and A points to B, and L-seg BC entails L-seg AC. So basically it says a list segment can be extended from the left, and this is provable with a single application of fold proof rule. And the second entailment that we want to prove is this entailment that says LSEG AC star C points to B star B points to nil entails LSEG AB star B points to nil, which is basically saying a least segment can be also extended from the right. And this entailment is true in separation logic, it is valid, but it's not provable by any amount of fold-and-fold reasoning. So no matter how hard we try, using only fold-and-fold, we can prove this entailment. And one way maybe to understand it is that the syntactic shape of the LSEG definition only allows reasoning from the left side. Another way to say the same thing is maybe that any application of fold-and-fold proof rules on this entailment will never produce something with the shape of A points to T and LSEG TB. But I think that you all agree that these two explanations aren't very satisfying. So it's not really clear why we can't prove this, right? And we really want to know, like the point of this paper is to understand why we can't prove this entailment with fold-and-fold. And more general, and for other entailments, can we identify those entailments that are not provable using fold-and-fold? Okay. So the high-level abstract answer is that fold-and-fold reasoning captures weaker semantics than separation logic, right? And weaker semantics means more models. So when we think of the entailment, we think of the set or the class of models of separation logic, and if for every model in that class the entailment holds, then the entailment is valid, but fold-and-fold considers more models. So there exist rogue counter models, so models considered by fold-and-fold reasoning that are not true separation logic models, and in those models, and they violate this entailment. So they're not considered by, and they violate the entailment. So that's the high-level answer, and for the rest of the talk, I'm going to give a bit more concrete answers. So I'm going to introduce weak separation logic, which has weaker semantics for separation logic, and crucially, fold-and-fold is sound for that logic. So fold-and-fold reasoning must consider all of the models considered by weak separation logic. Then I'm going to talk a little bit about rogue models of weak separation logic, how to find them automatically, and also I'm going to answer this question, do they capture all failures of fold-and-fold? So do all the failures of proving something with fold-and-fold are captured by these models of weak separation logic? In other words, is fold-and-fold complete for weak separation logic? Then I'm going to talk a little bit of the practicality of those rogue models and then conclude. So what is WSL, weak separation logic? So it's a logic, it's a weaker semantics that relaxes key requirements of separation logic with inductive definitions that are incomplete. So in weak separation logic, heaps are allowed to be infinite and not just finite. In weak separation logic, interpretations of inductive definitions are allowed to be any fixed point and not just least fixed points. And also, we relax the semantics of background theories in weak separation logic, and you can see the details in the paper, but for this talk, I'm gonna ignore background theories. And all of these relaxations mean that weak separation logic has strictly more models than separation logic. And we have this theorem that fold-and-fold reasoning is sound for weak separation logic. So when we reason with fold-and-fold, we must consider all the models of weak separation logic. And to really reiterate and drive this point home, so when we look at an entailment, we have this world of models of separation logic that we think of. But actually, when we use fold-and-fold, there's this larger world of WSL models. And we have these models in the difference, these rogue models. And when there's rogue counter models, so rogue models that violate the entailment, this will lead to failures of fold-and-fold reasoning. Okay. So let's see this in practice, going back to this entailment that we were not able to prove. and we can look at the rogue counter model for it. So it looks like this. We have an infinite heap, where we have the heap locations A, C, B, nil, but also these infinite heap locations 0, 1, and so on, that are where A points to 0, points to 1, and so on. And in this rogue counter model, we have this LSEG relation between A and C. So LSEG AC is true. And this is justified because LSEG 0C is true. And that is justified because LSEG 1C is true, and so on and so forth. And you can see this is not a least fixed point interpretation, but it is a valid fixed point. And conversely, we have none of these relations. So there's no LSEG AB, no LSEG 0B, and so on. And this is also fine, right? These relations won't exist in a least fixed point, so they don't have to exist in any fixed point, right? It's not the greatest fixed point, it's just some fixed point. And you can see that this model satisfies the antecedent of the entailment, but does not satisfy the consequent of the entailment. Great. And this model is an actionable explanation of the proof failure. So why is it an explanation? Well, if you believe that fold-and-fold must take into consideration weak separation logic models, and if you agree that this is a valid weak separation logic model, then obviously this model violates the entailment, and thus the entailment is not true for the kind of reasoning that fold-and-fold does. And why is it actionable? Well, maybe looking at this model helps you understand that there's something funky going on with LSEG AC, and maybe we need induction there, right? There's infinitely many elements that are in relation, LSEG relation with C, so maybe induction would help. So hopefully I've convinced you this model is useful. So we have two questions. So one, how can we find it, and find it automatically maybe? And second, does this characterize all proof failures of fold-and-fold, and so must it exist when we have a proof failure? So the first step we took towards finding these models is moving the problem over to first-order logic. So first-order logic is where I feel at home, so I wanted to move the problem there. And we have this model-preserving translation between entailments in weak separation logic and sets of formulas in first-order logic. And we have this theorem that there exists a model-preserving translation from weak separation logic entailments to formulas in first-order logic for some fragment that we call the effectively determined heap fragment of weak separation logic. But this fragment it's a large fragment. It contains inductive definitions, background theories, and it also allows some quantification in the entailments themselves. And from all of the real-world examples that we looked at fell into this fragment. So it generalizes existing and similar encodings that were more ad hoc, but it's like a general formal translation between weak separation logic and first-order logic. Okay, so once we are on the first-order logic side, we can use the existing tools and techniques of first-order logic, and specifically the formalism of symbolic structures, to represent and find those rogue models. So looking again at the model that we had before, it can be compactly represented using this symbolic structure, where all of the infinitely many heap locations between A and C are represented with this one summary node in the middle. And I'm not going to go too much into what is a summary node, but basically it represents all of this. It's just a representation of the exact same model that we had before. And again, the summary node here, which is infinite, gives you a good hint that maybe something weird is going on and you need induction around that summary node. Okay. So this was how to find them. Now, do rogue models of WSL capture all fold-and-fold proof failures? And the answer is yes. So we have the theorem that fold-and-fold reasoning is complete for the quantifier-free, theory-free fragment of weak separation logic. And we have this nice proof, but notice that entailments are quantifier-free, but we still have quantifiers in the inductive definitions. And we have this nice proof where we show this through a series of equivalences. So an entailment with inductive definitions is valid in weak separation logic if and only if some set of formulas is unsatisfiable in first-order logic. And this is exactly our model-preserving translation. Then, using tools of first-order logic, like Herbrand theorem and compactness, we know that a set of formulas is unsatisfiable if and only if a finite set of ground formulas is unsatisfiable. And then we have this lemma that identifies a finite set of ground formulas in first-order logic with a finite set of fold-and-fold proof steps. And the result of this loop is that we can conclude that indeed entailments with inductive definitions are valid in weak separation logic if and only if there exists a finite proof with fold-and-fold reasoning, which means that fold-and-fold is complete. Great. So this means that all proof failures of fold-and-fold are due to the existence of rogue WSL countermodels. So there's an equivalence between the two. And basically, this fragment of quantifier-free, theory-free is the best we could hope for when we think just of fold-and-fold reasoning, because fold-and-fold by itself can't do any background theory reasoning and can't do any instantiations of quantifiers in the entailments that are not in the inductive definitions. Okay, and beyond the completeness result of fold-and-fold, actually, the translation that we introduced works for the entire EDH fragment, which goes beyond theory-free and quantifier-free. And this gives a proof, complete proof mechanisms for the entire EDH fragment that goes by translating to first-order logic and then using a complete proof system for first-order logic. So the effectively determined heap fragment admits a complete proof mechanism. Okay. So we took these ideas and we implemented them in a prototype tool where we take entailments in weak separation logic or in separation logic, syntactically these are the same, and we translate them into first-order logic, and then we apply our symbolic model finder to try and find counter models to these entailments. And we ran the tool over the SLS benchmark, which is a benchmark of entailments in separation logic with inductive definitions. It has over 700 examples divided into several parts. And for one of the parts, we found rogue counter models for 92% of the examples. So some parts have actually entailments that are valid also in weak separation logic, and in those cases we can't find rogue models. Other parts use a lot of background theories, but for one of the parts, which is mostly just inductive definitions, we found 92% for the example counter models. Okay. So to conclude, I talked about how fold-and-fold does not capture the precise semantics of separation logic with inductive definitions. I introduced weak separation logic, which gives weaker semantics to separation logic with inductive definitions, which talked about how fold-and-fold is sound and complete for weak separation logic. So basically, that logic is the logic of that reasoning mechanism. I talked about how the larger EDH fragment is also complete, and the heart of these results is this model-preserving translation from weak separation logic to first-order logic. Also, I talked about how this can be used in practice to see why specific entailments are not provable, and we have a tool to automatically find these counter models, and that's it. Thank you.
Hi. Hi, thanks for the interesting talk. So I was wondering, in the example that you show, you could basically do it with induction, and then the two things that you remove in weak separation logic are the two sources that would give you an induction principle, right? the finiteness of heaps and then the least fixed point interpretation. So if you add basically an induction principle, would you recover the completeness, or do you think it would still be incomplete, but for some other reason?
So it would still be incomplete. There's no like one induction principle that we can do or a schema of induction principles that would work for everything, and it stays incomplete. So even with these principles, there's no complete proof system for separation logic with inductive definitions.
So would you have an example?
Not at the top of my head.
Oh, we can take it offline maybe.
Just a quick follow-up from that. I mean, it seems a bit strange to me that you have a system in which you have inductive definitions, but no induction principle for reasoning about them. I mean, shouldn't they go together?
So usually in separation logic, when you work with inductive definitions, you do have like actual tools use inductive rules, but they're not complete. They still don't give you a complete proof system. And we wanted to focus on like the basis of these tools, which is the fold and fold, which has no sense of induction. And maybe this explains why in weak separation logic we have any fixed point and not just least fixed point.
Hi. So you said that in 8% of your examples you cannot produce a counter model. Is it because your tool can diverge, or is it because it always terminates but it can't take very long?
So some examples might be valid in weak separation logic, and in which case our tool sometimes is able to say this is valid in weak separation logic, but sometimes even when it's valid, it can't because it's not tuned to that. The other thing is that there's not always a symbolic model that represents a row contour model. So you can't find all models that exist, and in that case, the tool, like you said, diverges.
On program logics and semantic frameworks. Today we have quite a range of topics. We have some linear logic, we have some abstract interpretation, some operational semantics, some incorrectness logic. Please come in. And for our first talk, we are hosting Marco Campion from University of Sorbonne that is going to talk to us about abstract interpretations.
Thank you. Okay. Okay, so error propagation in numerical analysis refers to how perturbations in the input data affect the output of a computation, and also how these perturbations are affect the subsequent computation of other computation. And this reasoning can also be applied to abstract interpretation in general. So, for instance, considering an abstract interpreter, we can consider how perturbations to the input data of the abstract interpreter, how these perturbations are propagated by the abstract interpreter in the output, and how this perturbation is propagated while analyzing the program inductively on the syntax. So what we want to show in this talk is actually that it is important to study error propagation in abstract interpretation, because we want to show that in order to study the imprecision generated by an abstract interpreter with respect to a concrete computation, the notion of error propagation, so the notion of this propagation of the perturbation, is essential. So why? Well, because if we have an abstract semantics which is precise with respect to a concrete computation, so we have in this case completeness with respect to a program P1, and we have also that the abstract computation is precise with respect to the program P2, then we get at the end that the composition of the two programs, the abstract interpretation of the composition, is also precise. The problem is that if we have imprecision over the first program P1 and another imprecision over another program P2, what will be the result? So how this imprecision propagates in the computation, in the sequential composition. So we want to show here that understanding how error is propagated by an abstract interpreter is essential in order to understand how it is imprecise an abstract interpretation with respect to a concrete computation. So here, the error propagation of the abstract interpretation of the program P2, which could be propagated, for example, linearly, so we have a kind of Lipschitz continuity, or in a cubic way. And in general, actually, we model this error propagation through the notion of omega continuity. So the notion of omega continuity applied to an abstract interpreter. So our contribution is twofold. I will show actually that I will propose an omega continuity logic that could derive on the structure of the program this omega, so this modulus of continuity, and then we will use this omega continuity notion in order to derive the imprecision of an abstract interpreter inductively on the program syntax. Okay, so we'll start with the definition of the omega continuity with respect to a semantics of a program. So the ingredients are partial order sets over a domain D and a distance of interest over the elements of this partial order. So we require that this distance satisfies the F identity and the triangle inequality. And also we require a form of compatibility with the partial ordering. So why? So the first two axioms actually represent, says that the matrix is actually a quasi-pseudo matrix in mathematics, while the last axiom actually requires a form of compatibility with the partial ordering, because it requires that the distances between the two extremes of a chain is always greater than the distance between intermediate elements. So this is essential in order to understand the imprecision over a chain of elements. So let's see an example of a classic distances over partial ordering, especially over abstract interpretations. We have, as a domain, we consider the domain of intervals, so finite and infinite intervals over integers. And as a distance, we can consider, for example, the counting distance, which is the absolute value of the difference of the cardinality of two intervals. Or, for example, the volume distance. So if we have like an hyperrectangles, in the domain of hyperrectangles, we can consider, for example, the absolute value of the difference of the volume. So in abstract interpretation, for example, we want to understand what is the difference between the volume of an invariant, of an abstract invariant with respect to the abstraction of the concrete invariant. So what is the general definition of omega continuity to a general function f over a partial order? So we have this omega, which is an order-preserving function, which is 0 at input 0. And this omega is called the modulus of continuity. Then we have a function over the partial order d, and we say that this function is omega continuous whenever the distances of the output, so of the result of the function, is always bounded by the omega applied to the distances of the inputs. In particular, we can instantiate this definition with the program semantics. So we get an omega continuity definition over the semantics of a program that I'm going to define in the next slides. But in particular, what I want to define is to try to derive this omega inductively from the syntax of the program. So I will consider as a toy language for the rest of the talk, the language of regular commands. So we have the basic commands, so the skip, assignment, and the Boolean guards. And then we have the program actually. So our regular language is composed by the composition, the join, and the clean iteration of the program. So as a syntactic sugar, we can build an imperative language with the if then else or while do. Then we consider a complete lattice and an order preserving semantics over the basic commands. So here the standard definition, we have the composition of two programs. We have again the join, so the O plus is the join. Then the clean star is simply the infinite join. Yes, is the infinite join of all the possible iteration of a program P. So how can we derive this omega through the program the program structure in order to derive a definition of omega continuity for the program semantics? So we'll define now the logic that we propose. So the logic is composed by three base rules. We can say three simple rules. So the base case, which says that if we have an omega continuity proofs of the base case of the base commands, then we can derive, of course, the omega continuity of the role semantics of the base commands. We can weaken the modulus of continuity omega with a bigger omega, and we can compose two programs, and we obtain as a new modulus of continuity the composition of the two functions. So the joins here is more tricky because we need to consider the distance between the join of the computations. So in this case, the join is obtained by applying a join bound operation over the two modulus of continuity of the program P1 and P2. And this we show that this highly depends on the structure of the domain and the distance that we want to use. So in this case, consider this scenario. So we have four elements with the distances between x and y, then z and v. So what is the distance between the join of the respective elements? So we need a definition of a join bound, which poses a limit on this distance, which depends of the distance on the x and y and z and v. So this highly depends on the domain and as the distance that we choose. For example, if we consider the domain of intervals, as we shown before, and we consider the distance that counts how many more elements has one interval with respect to the other, so we do the absolute value of the difference, then we can choose as a sum joint bound that respects the definition is a sum. So we consider the sum, and the same happens, for example, with the volume distance. Finally, we have the rule iterate for the clean iteration that is simply apply an infinite number of join to the omega continuity in order to derive the modulus of the continuity. So let's see a very simple example. We consider the absolute value, the program that calculates the absolute value of an input. So we want to calculate the modulus of continuity of this program with respect to the abstract semantics over the intervals by consider as our distance function will be the distance which calculates the absolute value of the difference between the cardinality of two intervals. So we use the logic that we propose in order to propagate the omega through the program structure. We start with the base case by considering the guards and the assignments. We get that here the distance is not modified, so we have the identity as an omega continuity. Then we can combine the two with the sequential rule, which still it is an identity. We can do the same here with the right part of the join of the program, and then we can apply the join. So with the join, we obtain, since we have chosen the distance, the counting distance here, we know that we can do the sum of the two omega, and so as the final omega modulus of continuity, we can do the sum of the previous one. So we get 2t as a final omegas, as a final definition, which is so this one. Okay, so let's see why it is important to understand how program semantics, how an abstract interpretation propagates this perturbation. So I want now to use this information in another logic that actually propagates the imprecision of the abstract interpreter with respect to a concrete computation in this case. So now we are in the abstract interpretation framework, and we call this logic the error propagation logic. So let's put a bit of context. We have the abstract interpretation framework. So we have a concrete computation over a concrete domain, which could be like this concrete computation could be uncomputable. Also, the concrete elements could be something non-decidable. And we have an abstract computation over some approximation of the concrete domain. And we assume that this abstract computation is sound. And we assume also a Galois connection between the concrete and the abstract domain. So what is the most desirable property in abstract interpretation is completeness. So whenever we have the equality between the abstract interpretation and the concrete and the abstraction of the concrete computation, we have completeness in this case. And I will indicate completeness with this symbol, with this big C. So the blue will be the concrete computation, while the green, I will also use the green for the abstract computation. Why completeness is a problem in general in abstract interpretation? Because when we consider an abstract computation, which is an always terminating computation, for example, in static program analysis, and as an abstract domain, when we consider a set of decidable properties, completeness is a very hard property to achieve, or even impossible. So instead of studying completeness here, we want to study the imprecision. So we want to study the difference between the invariant calculated so the result calculated by the abstract interpreter with respect to the abstraction of the concrete interpreter, and this imprecision we quantify by a distance. So by the distance that I have defined before. In particular, what I'm interested is understand what is the imprecision for each input that we are going to analyze. So I want to prove this inequality. So for every input, I want to know an upper bound of the imprecision with respect to that input. So I want to calculate this function, this bounding function, over the inputs of the concrete domain. So I would say that whenever we have this bounding function E, so when this inequality holds, I will say that the abstract interpreter is E partial complete, is an E partial complete approximation with respect to the concrete computation. And I will use this symbol, so this big C with the E, in order to to define the partial completeness with respect to the concrete and the abstract computation. So let's see a very simple example. We consider again the interval domain. We consider the counting distance. As a concrete semantics, we consider a standard reachability semantics over the power set of the integer. And then we consider a standard interval semantics, which the two domains of the power set of integer and the intervals are related by a Gola connection. So I want to analyze the imprecision generated by the interval analysis with respect to the concrete computation for the program, for the absolute value program. So I want to understand what is this difference between the two invariants. Can I derive this bounding function for every possible inputs? So in general, we can note that the worst case is when, as an input, we have two numbers with the opposite sign. So in this case, the distance is for example, -7, 7. As input, we get a distance 7 because the abstract domain, the abstract computation produces 7 more elements with respect to the concrete one. So we have imprecision. And in general, we can model this imprecision for all inputs by defining a bounding function, which simply say a sound bounding function, which simply states that the result is the maximum of a set whenever this maximum is positive. And so we can say that the abstract interpretation over the interval of the absolute value is an impartial completeness approximation, complete approximation of the concrete computation. So the problem is now try to derive this bounding function inductively from the program structure. So how can we obtain this bounding function over the program without actually knowing without actually executing the program or analyze? In fact, we are analyzing the program analyzer in this case. So we propose a neural propagation logic, which requires a program. We have a program P. We have an input over the concrete domain. We have a concrete semantics, so over a concrete domain, and an abstract semantics, a sound abstract semantics over an abstract domain. We have a distance of interest, so we decide the imprecision that we want to measure with the distance. What we want to derive is this predicate, so E bound. And this predicate holds whenever this function provides an upper bound of the imprecision over all the elements that are in this chain, from G to the closure, so to the abstraction of G. In particular, as a consequence, if we can derive that the imprecision over this input G is 0, then we can also say that the abstract interpreter is precise, can precise analyze all the elements over this chain. So let's start by, I will show now all the rules. In particular, we have the base case. So we assume that we have a derivation. We assume that we have a predicate for the base commands. Then we can apply the switch, so we can change the input of our abstract interpretation, and we can consider here as a derivation the minimum of the imprecision that we derived over another input. And then we have the sequential composition that is the key point here, because in order to derive the distance between the concrete and the abstract computation, we need to understand this chain of computation. So the results of the imprecision can be obtained by a sum between the imprecision generated by the abstract interpretation of program P2, where here we combine the result of the two computation by using a partial coordinates tripole and an incoordinates tripole. So here we use the imprecision generated by the abstract interpreter P2, and we sum with the propagation of the error that is produced by the abstract interpretation over the program P1, propagated by the omega continuity of the abstract interpreter P2 that is part of the logic. So this is the final bounding function derived in the logic for the sequential composition. For the joint bound, in this case, we consider here the same joint bound that I've defined for the omega continuity. Here it is applied here to join actually the imprecision over the two computation. While for each iteration here is a little different, because in order to calculate the the distance between the result of the concrete and the abstract computation. Here, I will consider another approximation of the concrete computation with post, and an over approximation of the abstract interpretation. And so I can take as a sound distance here the distance over the whole chain, over the whole chain of elements. So I will show a final example. Let's consider the sequential composition over the absolute value program and the clean iteration of this program F. So I want to calculate here the difference between the distance, so that I want to calculate here the distance between the abstract interpretation over this program, over the boxes, and the concrete computation, starting from an input G, which is only 2 points, which when they are abstracted are a rectangle. And I want to use the area, so I want to calculate the difference in the area of the invariance. So here I will start by inferring, so I will start by deriving the omega continuity of the program F. So we have the base case for the So we have the base case for the Boolean guards and for the assignments. Here we combine with the sequential composition. We get a quarter of t, and then finally with the iterate we get 4/3 t for the clean iteration of the F. Then we apply the iterate from the error propagation logic in order to obtain the imprecision of F star, of the clean iteration of F. And finally, we use all the information that we collected in order to apply the sequential composition between the two programs. So at the end, we obtain an area of value of 52. So what does it mean, this number? It means that the difference between the area of the two invariants is limited, the upper bound is 52. This bound could be also imprecise because we used as another approximation, we use a single computation of the concrete, a single iteration of the program F in this case. So we can improve this result by applying by using a more precise under approximation in this case. So by concluding, we propose an error propagation logic, which is the combination of correctness, incorrectness, and omega continuity logic in order to understand the imprecision of an abstract interpretation. And so we provide a way to formal model the imprecision of abstract interpretations. Thank you.
Yeah, so thanks you for the talk. I was just wondering, when you show like the join bound, the operator that combines the joins, like you showed a diagram that looks like kind of triangle. So I wanted to ask, can you give us an intuition why you can't like derive, like you need an operator that is specific for the domain, and it's not like just generic using, I don't know, triangle inequalities?
Okay. Well, in fact, here the join bound here is very dependent on the domain and on the distance. So in fact, you have to prove that if you want to use a join bound soundly in the program logic, you have to prove that actually the join bound respects the definition that I provided in this case in the paper. So it respects that the distance between the two joins is always it provides an over approximation of the distance of the two joins over the elements.
Okay, I see. Thank you.
I was wondering what abstract domains you applied this to, and what the join bounds looked like for them. Which ones lose a lot of information and which less?
So in our examples, we used only numerical domains. And so we applied them to like the standard ones, so like intervals, hyperrectangles, and octagons. And so the problematic point is when, of course, you use the widening. Because as soon as you apply the widening, you get like very easily like infinite imprecision. So in order to understand how the imprecision propagates, we consider like a kind of threshold using a threshold widening to see like finite imprecision, how it evolves in the computation. So we consider in this case only the numerical abstract domains.
We have time for one more question.
Thank you for the great talk. So is this also applicable to abstract domains that are not numerical?
Yes, actually we formalize everything by not requiring numerical. So what we only require is like an order preserving concrete computation and a sound abstract computation, not necessarily order preserving. So we don't require any numerical domains. It could be generalized.
Okay, thank you.
All right, let's thank the speaker again. Because we have time to set up. Sorry, this one is taken.
It's all good?
Yeah. Our second speaker for this session will be David Kahn, who is going to present us a new flavor of operational semantics, halfway between big step and small step. In a minute. Time to find the slides.
Plugged in.
HTML.
Yep.
Thank you.
Are we there? Ah, there we go. Well, hello everyone. I guess without further ado, let me tell you a little bit about big stop semantics. So this is talk is going to start with just a quick little recap of some of the classic bangers of operational semantics, and which is what everyone in this room probably knows and loves. So I'm going to start with the small step semantics. Those came on the scene around 1981 with Plotkin's structured operational semantics. And the way that small step semantics specifies the behavior of a program is by specifying the very next step that that program will take. All right. And if you want to express longer computations, all you do is you chain together a sequence of these single steps. So for a quick example, 1 plus 2 plus 3 plus 4 takes a single step to 3 plus 3 plus 4, 3 plus 7, and then 10. That's small step semantics. Now let me tell you a little bit about the other big player in operational semantics, and that would be big step semantics. And that came on the scene around 1987 with the work of Gilles Kahn, no relation. And unlike small step semantics, big step semantics works by trying to directly relate an expression to its resulting value. And the way that it does that is by breaking up an expression into meaningful chunks and reasoning about how those different chunks evaluate. So for example, the same previous expression we just looked at has these two significant sub-expressions, and they evaluate to 3 and 7, so the overall expression evaluates to 10. Great stuff. Now, big and small step semantics are usually considered to be equally good for specifying the behaviors of programs, and you might have even encountered a theorem like this in some undergraduate course that explicitly says that the expressivity of both of these kinds of specifications are equal. But there is a small caveat to this theorem that is somewhat easy to overlook, and that is that it only holds for terminating expressions. To see why, consider some E0, which is an expression with a non-terminating execution. Small step semantics can work with E0 with no issue. It can just keep stepping along as far as you would like, and as a result, it can capture all finite prefixes of this computation. This is a happy circumstance, because it is sufficient to prove invariance about the program's execution, such as, for example, type preservation. And this holds even for infinite computations as well as finite computations. It covers all kinds of programs uniformly in that way. On the other hand, big step semantics immediately gets stuck. It can only relate an expression to the value that its execution terminates with, and E0 just doesn't terminate. Thus, big step semantics simply does not define the computational behavior of programs that don't terminate. This is not a very happy circumstance. as it means big step semantics cannot be used for verifying properties of such non-terminating expressions. As a result, whenever non-termination is on the table, people often reach for small step semantics. Now, the thing is, non-termination is often on the table, or at least the ability to run a program indefinitely, if not infinitely. And this matters. For example, consider a web server for a website. When you log on to your favorite website, you would hate to find that the program on that server has just terminated and that website is inaccessible. Or perhaps more seriously, consider a medical device. That needs to be able to run as long as it needs to help the patient. An airplane. If an airplane gets diverted from its path and needs to stay up in the air a little bit longer, you would hate to have that flight control program terminate its execution. And for maybe an application that's a bit more in focus in this community, if you're going to make a compiler, you just kind of have to put up with the fact that people can write infinite loops. And the thing is, while true, should not set your compiler on fire. Undefined behavior just isn't good enough for fully specifying the behavior of a programming language. And just isn't good enough, therefore, for formalizing a compiler. So we can't use big step semantics for this purpose. So if we wanted to pick out an ideal operational semantics, the first item we might put on our wish list is this, that we can handle all programs, terminating or not. And we'll add to this list as we go through the talk. So sure, it's true that big step semantics is inadequate when it comes to non-termination. It just doesn't satisfy that item on our wish list. But so what? We can just use small step semantics, right? And indeed, nothing stops us, but it would be a lot nicer if we didn't. Anecdotally, and even with a lot of data to back it up, many people in this community have pointed out that big step semantics is just nicer for the proofs of many program properties. The big step rules themselves are usually more concise because they don't have to deal with all the baggage of congruence rules that small step semantics has, which can make it a little bit easier to set up a proof. And more importantly, the proofs using big step semantics tend to follow by direct rule induction over the derivation of the operational semantics. Whereas for small step semantics, the proofs are often quite indirect and can sometimes require some non-trivial invariants. So while it may not be a hard and fast rule that big step semantics leads to nicer proofs, it certainly leans that way on many of the proofs that I am interested in. And so I'll put a second item on this wish list. It would be good if we could maintain some of the niceties of big step semantics, especially with respect to proving. So rather than use small step, it might actually be worthwhile to look back at big step semantics and find a way to salvage its use for potentially non-terminating programs. And the thing is, we aren't the first to have realized that this would be worthwhile. Let me just tell you a little bit about some prior work. The vast majority of it is based on co-induction. And this started at least with Cousseau and Cousseau in '92, and many, many more have built upon the same basic idea since then. To give you the basic flavor of this approach, here's just one rule that might come up for function application. To co-inductively establish that an application of the expression E1 to E2 is non-terminating, that's that infinity symbol, it suffices to co-inductively establish that E1 is already non-terminating. And the derivation for E1 would need its own non-terminating premise ad infinitum. And this approach works just fine to co-inductively pick out non-terminating expressions, as witnessed by just how much work is built off of this approach. But just because an approach works does not necessarily mean it is the easiest to use in practice. Even if you are already comfortable using co-induction, it can be non-trivial to mix co-inductive definitions with inductive ones. And this non-triviality is also probably why many proof assistants have had issues supporting co-induction. So even if you are working in formal verification and want to use co-induction, even if you stick to the rails of your proof assistant, you sometimes need to be careful because things can go wrong. So for these reasons, it might save us some headache if we could instead pick a purely inductive system. So let's add that to our wish list. So then maybe we should look at some prior work that is inductive. And the thing is that there really hasn't been all that much. One example is what are called partial proofs. And these add two mutually recursive judgments to the semantic system. One is the redex judgments, which progress the derivation, and one is the search judgments, which don't. And these judgments range over values and as well as some special meta-variables called logic variables that stand in for incomplete derivations. Another different line of work is the work that uses step counters. These step counters are used as fuel, and the way that they affect the semantics of the program is that when the fuel eventually runs out, the program will immediately terminate with an error. And this prevents running for indefinite lengths of time because you only have finite fuel. An example of such a rule in this system would be the following, again for function application. And what this says is that if you're going to run out of fuel when you're computing E1, then you're going to also run out of fuel, even if you have one more fuel, when computing the application of E1 to E2. All right, so that's just two examples. And while all of these inductive approaches do work, you'll notice that they all end up imposing some extra proof obligations to deal with all the extra things that they add to the semantics. In the case of partial proofs, you have to juggle multiple kinds of judgments and now multiple kinds of variables. And in the case of fuel, one often needs to quantify over fuel amounts and then discharge that quantifier. It is important to know, for example, that computation is sufficiently independent of the fuel amount as long as you have enough fuel. So that brings us to, I guess, the final item to add to the wish list. It would be good to have just a simple, single kind of judgment that doesn't add a whole lot of new pieces to deal with in the semantics. Ideally, we want something minimally invasive that is almost just the big step semantics, so that our proofs remain just as easy. Now, there is actually one other piece of prior work that I haven't mentioned yet, and that is the partial big step semantics of Hoffman and Hoffman. So this work can capture non-terminating programs inductively in a big step style, which is almost everything on our wish list. But like the other inductive work we saw, it isn't quite all that simple. You see, this work is specialized for giving the cost semantics of a functional programming language. And to do this, it actually augments its judgments with quite a few things, counters as well as heap and stack. But unlike other work, these augmentations don't actually play a big role in how the system reasons about non-terminating computations. Instead, what this approach does is it adds a whole new specialized judgment to represent a partially complete evaluation. And then the semantics allows non-deterministic halting with this new judgment so that a program can sort of stop at any point and recount the cost it has accumulated so far. And I had actually been working with this system for quite a bit in some of my other work when I eventually realized there was quite a lot of room for taking this non-deterministic halting idea a bit farther. In particular, it might be possible to get the same result more generally and more simply, getting every item on the wish list. And somehow it doesn't seem to have been done before. That leads us to big stop semantics, because it maintains the core idea of partial big step semantics, which is the ability to non-deterministically halt or stop. And this is going to give us everything that we want on our wish list. So let me start by showing you an example of how simple it is to turn some big step semantics into big stop. And I'll do that here for a simple PCF-based language as displayed. These are the big step rules, but I don't want you to care too much about any of their details. I just want you to see that here on the top, we have some of the basic computational redex rules. You know, we have recursive function application. We can case on natural numbers. And then on the bottom, we have the remaining rules, which are basically values and congruences on values. To make this big step system into big stop, all we need to do is make the following change to the rules. Boop. And this is one singular new rule schema, and it captures what it means now to non-deterministically stop. Let me show you exactly how it does this by instancing it on the stopping rules for function application. So there are three ways that function application can stop. First, it can just immediately stop. And that will leave the left and right side of the judgment the same. And in fact, the stopping rule is set up so that every expression can big stop to itself, which is why we no longer need a separate rule for stopping values. The second instantiation is that we can begin to partially evaluate the first sub-expression, here the function E1. And you can see how that partial evaluation E1 prime takes the place of E1 on the right. This kind of behavior is why we no longer need separate congruence rules. And finally, we have the ability to partially evaluate the second sub-expression, but only after fully evaluating the first. This ensures that we maintain the order of operations that the language demands. So these are the ways that an application can non-deterministically halt, but do note that an application could also just evaluate as normal. It's all non-deterministic. The key reason why this non-deterministic stopping actually works can be seen by recalling small step semantics for a moment. In particular, how small step semantics handles infinite computations. Small step semantics lets us increment our computation one step at a time, allowing us to stop between any two steps if we so wish. And at that point, we can inspect the partially evaluated expressions that we find. Considering all the places we can stop gives us a very easy form of theorem statement. If we can stop at some intermediate point, then X holds there, where X is just whatever property we're interested in, like type preservation. And this shows that X holds as an invariant across all of computation, infinite or otherwise. So what does big stop semantics do? Well, the same thing. It just uses deeper and deeper derivations instead of taking more and more steps. And so big stop allows the same convenient form of theorem as small step. Just now, instead of having to work with cumbersome small step relations, we can capture all the same stopping points with a convenient big step style relation. And the equivalence in stopping behavior between small step and big step can be made precise with the following. If you can big stop to some expression E prime, then you can reach that same expression E prime with small step, and vice versa. And for good measure, we proved this theorem in AGDA. So now you might be wondering, so what? Doesn't this just show that you don't gain anything over small step? Well, the answer is that this equivalence shows that big stop can get the same theorems as small step, but now we can do so with easier proofs. And we actually backed this up a little bit with a case study. So what we did is we considered compiling our PCF language by tossing it into a Kriven machine, or K-machine for short. A K-machine is just a stack-based model of computation, kind of like the Zinc abstract machine, which underlies OCaml's bytecode interpreter. So this simple compilation actually has some real-world parallels, and we would like to verify that it is correct. Formally, that means that our PCF semantics describe some program behavior if and only if the K-machine describes the same behavior. And just to make things interesting, let's add in effects as well. That makes it all a little bit more real world, and also means that non-terminating computations can have observable differences, because we can look at the effects rather than just the resulting value. So here we have the terminating cases for proving that theorem. The first case for terminating programs is terminating soundness, saying that if the K-machine can show some behavior of the program, so do the big stop semantics. And then secondly, we have terminating completeness, which shows the reverse. And terminating completeness is actually the interesting one to look at, because its antecedent is the semantic relation. And so this is where we might induct over the derivation of the semantics. If we were using small step semantics instead of big stop, this theorem would actually pose a bit of a problem. See, the problem is that small step semantics forms chains like this, where the resulting expression E1 is also the input expression to another relation. And so in order to apply the inductive hypothesis, we need to search for a K-machine state that can properly correspond to E1. The problem is that K-machine state simply may not come up. There's not a good correspondence between the small step semantics and the K-machine. And so instead, the textbook approach to proving this is actually to just use big step. Turn small step semantics into big step first, and the proof proceeds by simple induction on the derivation. So that's all fine with the terminating cases. But what about the non-terminating cases of correctness? Well, we again have some non-terminating notion of soundness, which says that if we can partially evaluate an expression, inducing some effects, then we can do so with either the K-machine or our big stop semantics. They'll do the same thing. And non-terminating completeness will give us the reverse. And so again, completeness is the case that's worth looking at because its antecedent is the big stop semantics. But this time, neither small nor big step semantics is sufficient. Small step semantics has the same problem as before, but big step semantics can't formalize partial computations. So we would be stuck if not for big stop semantics. And so to finish off this correctness proof, we use what we call the big stop method. We start with the standard big step theorem. We extend its rules of the big step semantics into big stop. That gives us a very trivial terminating theorem because we already had the big step theorem. And we just need to add new proof cases for the stopping rules. The result of doing this formalization of the correctness, specifically for completeness, looks like the following. And I could talk about all these numbers quite a lot, but I'll suffice it to say that the big stop semantics shows that we can get all the results that we want for terminating and non-terminating programs with relatively few lines of code, especially compared to small step semantics, which is often twice as big. Now, the final thing I'll say is that for big stop semantics, you'll notice that the non-terminating proof is about twice as large as the terminating one. And this is because we used that schema, which breaks down into many different rules that we now need to cover. But in the paper, we also show you can optimize big stop semantics to require just one new rule. So here's an example where all of these rules are from the original big step system, and this single simple rule here is from big stop. And this is just a single simple rule, not a rule schema. And so that's all. The paper describes this big stop system, proves its formal properties, exhibits the efficacy of it with this case study. We show how we can optimize the number of rules we have to actually create. And we also show that it works in the paper, in the extended work, for like imperative languages as well. So it's actually quite applicable. That's all I have. Thank you.
So when you're talking about corresponding big stop and small step semantics, there is kind of implied assumption there is some states which are synchronized between the both. Is that correct?
I couldn't quite make out the end of that question.
You can hear me? I can repeat. When you're talking about comparing big stop and small step semantics and correspondence theorems, is there an implication that there is some states which must be synchronized between the both?
So for the theorems that we have proved for like the K-machine, we don't have any statefulness, but when we show in some of the extended work how to extend this work to, for instance, an imperative language, then we do have state. I'm not sure if that's exactly what you were asking. Is that
just quickly clarify. For example, you have a defined in big step operation with 3 arguments, plus and multiply, as a single thing, and in the small step it's 2 separate steps. You wouldn't be able to correspond them.
Yeah. It's a tight correspondence. They exactly represent the same relation.
We have another question on the other side.
Hello, thank you for the talk. I'm wondering if you lose inversion and if that makes any proofs harder with big stop semantics.
I'm sure that there are some proofs that end up being more difficult, but a lot of the proofs that one might be interested in, I keep thinking of type preservation, for example, tend to just follow more easily if we use a big step style approach. So while certainly, there's not necessarily any best proof system. I think big step-style semantics come up often enough as something that's cited as making proofs more easy for things like, for example, proving the correctness of compiler passes and such. I can't think of any good example where small step semantics is the better alternative.
And one more question before the next speaker sets up.
Thank you for the great talk. I'm curious if there was any prior work. I'm over to the left, but if there any prior work to show correctness for compiling to K-machine before big stop semantics. You said like it wasn't possible in small step and either impossible in big step.
There was some prior work on compiling to the K-machine. It's actually in the PFPL textbook. The problem with that work, in some sense, is that it's not effectful and has no hope of being so, because the most it can reason about is terminating computations for the exact same reason that I brought up in the talk.
Let's thank the speaker again. Our next speaker will be Michel Pagani, who will present us a linear logic for automatic differentiation. And once again, 1 more minute for the slides to come up. Good.
Does it work? Yeah.
Yes.
It's okay.
You can go ahead when it works. Yes.
Okay, so thanks. I'm Michele Pagani. Sorry. I will present a joint work with Giulia Giusti, which is about JAX encoding JAX automatic differentiation into linear logic. So JAX is a popular Python library for numerical computation, which offer functionality from automatic differentiation. So the general picture is here. So consider a program P computing a function over real numbers. And JAX offer functionals like grad that take P and transform it in grad P, which is a program computing the gradient of this function whenever it exists. Which are the kind of properties that we are interested in from a PL perspective. The first one is the soundness, of course. Is it really the case that grad of P computes the gradient of the original function? Another property is efficiency. So how much does it cost to evaluate the grad of P with respect to the original runtime of P? And along this point, there is, we have to mention the backpropagation algorithm, which is a specific algorithm which is at work behind the grad of P, which is quite efficient in the case the input domain of the original program P is huge. Well, could you repeat, sorry?
Differential linear logic.
Okay, so what are the links between this work and differential linear logic? So what I did here is to encode automated differentiation in standard linear logic, so there is no differential linear logic at all. The difference is that differential linear logic helps to generalize, to extend the linear logic so that we can speak about the derivatives at high order types. So until now, we are speaking about gradient and derivatives on numerical programs, so programs over real numbers. While in differential linear logic, we can speak about derivatives at the type of trees or the types of functional between natural numbers and things like that. So it's
by Flavio Ascari, who will present us a new analysis using incorrectness separation logic.
I am Flavio Ascari, and the work is on enhancing incorrectness analysis by reversing direction. So let's get started with the first question: what is incorrectness analysis? And I mean, the idea of incorrectness analysis is I give you this very simple program, and I ask you the question: can this program rise the error, and if so, under which condition? And this is different from, let's say, the usual kind of safety analysis that we do, because our goal here is to identify only real errors that you can find. So we don't aim to prove the absence of errors, but we want no false positive. If we show that an error can happen in our analysis, then that must be also true of the real program. And to do that, we change the perspective from over-approximation to under-approximation. A prime example of one such, let's say, under-approximation analysis is incorrectness logic. And like, roughly speaking, incorrectness logic does a forward analysis. So you start from some precondition that is true in this case that we call P. And you go through the program. And at the end, you reach some post-condition that contains some error. And what the condition, in particular, every error in the post-condition is actually reachable. And you can see it here in this, like we call the post-condition Q. So you have that all the error states in Q are reachable. However, the guarantee on the precondition is pretty weak, because in general, P may also contain some states, for instance, this one, that leads completely outside of Q. So you don't know that all, like, which are the conditions under which the error can happen in an incorrectness logic triple. A way to address this problem is to do a backward analysis instead. So in a backward analysis, you start from the error. Now you don't know that all the errors here are reachable, but by going upwards through the program, you end up in a precondition that is, for instance, in this case, y is equal 0, and you are guaranteed that from any state satisfying the precondition, so from any state in P, you have at least one execution leading to a state in Q. And so if all the states in Q are errors, every state in the precondition can lead to an error. Not that because of non-determinism, a state in P may also reach something outside, but it will definitely have at least one execution leading to Q. Of course, the drawback is that you don't know anymore that all states in Q are reachable, but this is, let's say, the trade-off on the two kinds of analysis. So this helps us in identifying the condition under which an error happens. And I have good news for you. A lot of people have already done backwards under approximation analysis. So, I mean, we have Lisbon triples, we have outcome logic, we have Unter, we have sufficient incorrectness logic. But I think there is still some issues with the backward under approximation. Not everything is completely settled. And I want to show you what the issue is with this example. So the example is still pretty simple. We initialize x, then we have this while loop, and in the end we get to the error. So basically the goal that we are trying to show here is that the while loop terminates. That's basically the problem here. Because if the while loop terminates, then we get to the error. And we start doing this with our backwards analysis. We say, OK, for the while loop, like we start from the error at the bottom. For the while loop to terminate, we need to have here some x that is equal to 0. And to do that, like we use an under-approximation technique that is a finite loop unrolling. Since we're under-approximate, we only care about some execution paths that lead to the error. So finite loop unrolling is a sound under approximation. And we have some heuristic that tells us, okay, let's unroll the loop 2 times. And so we know that if x at the beginning is a number between 0, 2, and 4, then the loop definitely terminates. And since x is equal to 4, it's assigned to 4, then we are happy every initial state lead to the error. However, the issue is that we would like to do this analysis compositionally. And since it is a backward analysis, this means that we analyze the while loop before we have seen the assignment to x equal 4. So we have this heuristic that told us to unroll the loop 2 times. But if we now change the assignment from x equal 4 to x equal 10, we expect our heuristic to tell us the same result, so that we want to unroll the loop 2 times. And if we still unroll the loop 2 times with this assignment, we get a false precondition that is, I mean, it is a sound under approximation, but it's not very informative. We don't like this result because it's not giving us any information on the initial states leading to the error. And what is the problem here? Well, the problem is non-determinism. And to be more precise, is the non-determinism in the unrolling of the loop. So let's talk a bit more about this non-determinism that is the problem. In general, when you analyze a program, you have 2 kinds of non-determinism. One is the program non-determinism. That one is, in a sense, more localized because it's usually introduced by, let's say, explicit constructs, either like data flow or control flow that introduces the non-determinism. And this is fine. It's part of the program. We will have to deal with that in some way. And there are ways to deal with the non-determinism in the program. But there is another kind of non-determinism that is the proof search non-determinism. So for instance, in the backward analysis that I've just shown, the non-determinism that we have is introduced by this while loop. Because while going backward, you can unroll the while loop any number of times. And so you have to non-deterministically choose how many times you want to unroll this while loop, right? And this is often solved by previous program statements, because if you are going forward, like you see that x is 4 before the while loop, and so you know that you have to unroll it 2 times. But as I said, since we're doing a backward analysis, we haven't seen these previous program statements yet, because they are in the future of our backward analysis. And there are other kinds of non-determinism introduced by the proof search. And one such example is given, for instance, by when you deal with pointers, you have this a lot. And I will show you a more concrete example later, but the point is here, even if you look at these 2 lines, we free y, and then we dereference x. And we have another kind of non-determinism that is introduced by the possibility of aliasing of x and y. So this statement may be an error if x and y are aliased, because we just freed y that is aliased to x. But it may also not be an error if x and y are just different pointers. And so, I mean, this is another kind of non-determinism that happens a lot, and it very quickly leads to a combinatorial explosion in the possibilities, because every time basically you use a pointer, you have to consider all the possible aliasing with all the other pointers that you're talking about. So our goal is to address only this second kind of non-determinism, the proof search non-determinism. And ideally, our end goal is a fully automated analysis. So we would like to give let's say, a way to completely resolve this proof search non-determinism. Before showing our solution, I would like to spend a few words on other approaches, because we are not the first one. As I said, many other people already worked on backward under approximation, and so other people proposed other solutions. And I think most of the approaches are based on a backwards valid forward analysis. So what they do is they do a forward analysis of the program, and this kind of solves the non-determinism because you see that x equals 4 before analyzing the while loop. But they do so in such a way that in the end produces a result that is also valid in a backward sense. So this is for instance, the approach taken by Unter, that is a work by Rad et al. Published 2 years ago. And this is an effective solution. It's the theory that is behind some real tool words, or it's an effective solution, but it still needs somehow either some guesses or to backtrack to kind of, let's say, retrofit some assumptions that you find out later that you needed to make the analysis backwards valid. So we propose a different approach to this one that is, as you might have guessed from the title of the talk, is U-turn. And the idea behind U-turn is to get us to do a smart sequencing of incorrectness logic, so the forward analysis, and the SEAL, that is like one of the names for the backward under approximation analysis that I showed you before. So the idea is that you take as input an incorrectness logic, so a forward derivation, and you transform this forward derivation into a proof strategy for the backward analysis step. And the point is that you obtain a fully deterministic proof strategy, so we completely solve the proof search non-determinism in the backward analysis. And to do so, we heavily exploit the fact that the forward analysis is done specifically for the program that we are trying to analyze. And so precisely because this forward step is for the program, this allows us to get a fully deterministic proof strategy for the backward analysis. And like, if you think of this in terms of like the pictures that I showed you before, let's assume you start with this precondition P, you do your forward analysis and you find Q, but in P there are also some of these states that don't lead to Q. So what you want to do is you want to kind of follow backward again the path you followed the forward before to find this P prime that is like a refinement of P that removes all these points that we don't really care about. So let's see how it works on an example. This is the same example from before, and as you might have guessed, the key idea is that, okay, there is this x equal 10 in the code. So in some sense, I should be able to know how many times I want to unroll the loop. And if you do a forward analysis, in fact, it is pretty easy to see that, like, since x is assigned to 10, you unroll this loop 5 times. So let's suppose we are given this forward analysis, and we now like use that as a guide for the backward analysis. And the backward analysis, we start again from the error and then arrive at this point, and it sees the while loop, and then like we have to decide how many times we want to unroll this loop. But the answer now is trivial, because like the only thing that we have to do is to go in the forward analysis and look how many times did the forward analysis unroll the loop, and the forward analysis unrolled the loop 5 times, and so we do the same in the backward analysis, and we find this x equals 0, and so we complete the proof. And note that if we change this x from this assignment from x equal 10 to x equal 4, then the forward analysis will unroll the loop 2 times, and so like even going backward again, we will unroll the loop 2 times, and so the things will check out. To go on a slightly more involved example, this one as pointers. So this is a model of the pushback function, the C++ standard library pushback function. So the idea here is this V is a vector. X is a reference to the underlying buffer of the vector. With the pushback, what may happen is that non-deterministically, if there is not enough space in the underlying buffer, we reallocate the underlying buffer of the vector. But this invalidates the pointer x, and so when we try to use x here, we get an error. So for this example, I will use the, let's say, assertion language of separation logic. If you're familiar with it, you probably know already what this means, but roughly it says that x is an invalid pointer, and separately, the rest of the heap can do whatever, so we are not really worried about what the rest of the heap does. We are only, like, the only thing that we require is that x is an invalid pointer. And this is our error condition, because if x is an invalid pointer, when we try to the reference, we get an error. So we just focus on the body of the pushback, and if we do our backward-only analysis, so this is without U-turn, this is just to show you what happens with the backward-only analysis, we get these assertions, and I want you to focus just on the free statement. As you can see, after the free statement, x is deallocated, and this can happen because of 2 things. Either x was already deallocated before the free statement, and y was a different pointer, so x and y are not aliased, or, and this junction means that these are kind of 2 program paths that we have to explore. And the second program path says that, okay, x was not allocated before. In fact, x was aliased to y, and before x was allocated, the same as y, but then the free statement introduced this deallocation. So in this very deterministic sequential program, we already have some kind of non-determinism that is introduced by the proof searcher. So I mean, this is really a problem that you see a lot when you try to do this backward analysis. And how does U-turn solves it? Well, For U-turn, we now assume that we have a forward analysis. And so if we analyze this fragment again, we will see that we will start with like our precondition in the forward analysis that says that V points to X because we see this assignment first. And so we will get this assignment where, like this initial state where V points to X and some other conditions, and then we go on, and then we go on with the rest of the analysis. And the point is that since we already know that V points to X at the beginning, when we do this assignment, it's trivial in the forward analysis to see that now X and Y are aliased, right? So the forward analysis kind of knows that X and Y are aliased. And so what happens when we do the backward analysis? Well, we start from the end, and we do one backward step before this assignment. So here already we get some information from the U-turn proof, let's say from U-turn. And you can see this because here we assign the thing pointed by V. So before, like when we only did the backward analysis, we could only say that V pointed to something. Like it would have been a sound thing to guess that V pointed to X because this is an under approximation. We can choose our path. But of course, like in general, like how do you guess that V points exactly to X? But in this case, we know that V points to X is the right guess because you can see it in the forward analysis step. If we go further with the backward analysis, we now see again something similar. We assign Y, so we had no idea about the value of Y before the assignment, but we can add this guess that X and Y are aliased. This is a sound again under approximation, but let's say the motivation why we add this guess is precisely because we can see it in the forward analysis. And this allows us, like in the previous step, before the free, to only consider the case where the two are aliased and no longer the case where Y is instead a separate pointer, a different pointer from X. And so, like in this sense, we solve the non-determinism by like, let's say, asking the forward analysis what we had to do. And so in the end, we get the full derivation for this program. So I hope the two examples gave you an idea of intuitively how U-turn works. Now to go a bit more on the, let's say, technical part for the last 5 minutes. In U-turn, we use judgments of this shape. So in the gray box, you have the forward derivation, the incorrectness logic derivation, and we don't only consider the final triple, PRQ, but we consider also delta, that is the entire derivation tree. So like, as I said, we don't look just at the result of the forward derivation, but we want the entire derivation. And we use this part in the gray box that is the input of the U-turn to guide the proof, the backward proof that is this P prime RQ prime. That is instead the backward analysis. And an example rule is, for instance, the if rule. So think of this as a backward analysis. So you start with this Q prime, and you want to find a suitable P prime for this if statement. And when you have an if, you have a choice. You can analyze the then branch, you can analyze the else branch, or you can analyze both. And when you have to decide which ones to analyze, to answer your question, you just look inside your input, inside your gray box, and you see, OK, the forward analysis decided to only analyze the then branch, only C1. So I will do the same. Also in the backward analysis, I will only analyze the C1 branch. And you will use, let's say, as input for the analysis of the C1, let's say as a guide, you will put in the gray box the remainder of the derivation that you had for the forward analysis. So you have this kind of rules. We have similar rules. For instance, this is what brings you to like the same number of unrolling in a while loop, because you will basically unroll as long as the forward analysis unroll the loop. So this is a proof strategy for the backward analysis, and you may wonder how good of a proof strategy this is. And we have a theorem in the paper that is that we call the progress theorem, that says given any incorrectness logic derivation delta, so whatever is let's say the thing that you put inside the gray box, then there exists a non-empty P prime such that P prime implies P, and you can prove the corresponding U-turn judgment. So if you look at it in terms of these pictures, it's exactly what I was telling you before. You start with this P that finds a Q going forward, and then you go back and you find this P prime that is a refinement of P that removes all the quote-unquote bad points in the initial state. And the proof is effective, is an algorithm to compute this P prime. we have a lot more stuff in the paper. We have a lot of rules. We have more examples. We have more comparison with this other approach that I mentioned before, the backwards valid forward analysis. And lastly, one thing I would like to focus on is the last point, is the fact that instead of just considering this idea of using a forward analysis to guide a backward one, we use the same shape of judgments to use the backward analysis as a guide to get a proof strategy for a forward analysis. So by using the same shape of judgment, we could also, let's say, combine the two logics in the other direction. And roughly speaking, this is useful because maybe you start from a set of errors that you think may be reachable, and you want to find both initial states leading to this error, but also to refine this set of errors to only find the ones that are actually reachable, because you don't want just to you guess the set of errors at the beginning. So to conclude, what we did in this work was to show how you can use a forward derivation to guide a backward one, or also to do the opposite. And in general, we also think that the shape of the judgment that we introduce, or this idea of combining proofs in different proof systems can be something that is worth exploring more in the future. And that was it from me. Thank you for your attention, and please ask questions.
Hi, thank you for the talk. So I'm curious if you can say how this approach compares to bi-abduction, where you also do a forwards analysis, but while you do the forwards analysis, you're refining the precondition.
Okay, so that's a very interesting question, thanks. By itself, bi-abduction is not exactly like an analysis algorithm, is more like a way to infer the precondition. So I will try to relate this with what Infer does, that is a tool implementing bi-abduction for this goal. So as far as I understand how Infer works, I haven't checked the code, but the idea should be that roughly that Infer uses some logical variables that keep tracks of the initial states, the initial values of basically everything that you have, and then by going forward, it adds some frames that you can add to the precondition that that only talk about these logical variables, and you can do that because the logical variables are not modified by the program ever, because they are logical variables. So in this sense, you kind of have this implicit relation that is given by whatever transformation you had during the program between the current value and the initial value, and you kind of add a frame talking about this. In our approach, what would happen is sort of like when you, for instance, you get a condition and you have to backward propagate that, you kind of actually just execute the program backwards, and you find out roughly the same condition in the initial state, but I would say more, let's say more, yeah, I mean, it's instead of in one sense you have the forward computation and then you put a condition on the forward computation. In the other sense, you start with a condition and you do a backward computation starting from the condition. So you get slightly different representation in the precondition of let's say the same constraint.
All right. One last question, maybe.
Sorry.
Yeah, go ahead.
Hello. Sorry.
Oh, okay.
I have a somewhat similar question. Well, first of all, that's really cool. Have you thought about how to automate / implement this into a tool? Because that seems like carrying around a proof tree is quite expensive.
Okay, so yeah, we have some idea, but we haven't worked on a full implementation, so it's just, let's say, theoretical rambling at this point. But the idea would be, instead of doing a full forward analysis, the thing that we were talking about is, okay, you start doing your forward analysis, but whenever you find one such condition that would require, in an incorrectness logic analysis, this condition, you can add them by using, for instance, the consequence rule. Whenever that would happen, start in parallel a backward analysis that backwards propagate that just, let's say, the they propagate that condition to the initial, let's say, to the precondition of the, for instance, of the function summary. And so like this would allow you to, well, first do this backward propagation in parallel. This is always nice. And second, like you should only keep like proof trees of relatively smaller part of the programs that are like matched to the summary that you're computing. That would be the idea.
That makes sense. Thank you.
All right, let's thank the speaker again. That concludes our session, and if you are more
Do I need to turn it on? Okay. Oh, welcome. Welcome to a short session, but a great session. So we have two speakers. Our first speaker is going to be telling us about dependent co-effects for local sensitivity analysis. So this is Victor Sagnier. Can we get his slides? Yep, okay. Go right ahead.
The introduction. So I'm going to talk about a notion we have introduced, which is dependent co-effect, in the context of local sensitivity analysis with applications to differential privacy protection. So I am first going to talk a bit about global sensitivity and why is it useful in the context of differential privacy before moving on to some type systems that have been introduced to analyze sensitivity and the links it has with linear logic. And then we will move to dependent co-effects, which are our main contribution before giving a few case studies. So first of all, about privacy for our motivation. The setting we're considering is the following. So you have a data analyst who sends queries to a database, and we want to be able to answer to queries that are for general concerns. So if it's the mean, the median, the standard deviation, or whatnot, we should be able to answer those queries, but not targeted ones. And to do that, just removing all the identifiers or strictly personal informations about the data in the database is not sufficient, as you all know. So instead, we would like to have a formal definition. And the most popular one is the following. It's differential privacy. The main idea is that the result of a query should be roughly the same for D and D prime, being two databases that differ by only the presence of absence of a single individual. So if you know everything about a database except that one single person is absent or not, you cannot learn anything, basically. So formally, you have some privacy parameter epsilon here, which acts as the maximum multiplicative difference between the probability of queries satisfying a predicate in either case. And one of the main reasons we study this property is because it is composable. So if you know that two queries are differentially private, then you will know their composition is 2 for a very wide definition of composition. So we can talk about sequential composition, parallel composition, and so on. So it's a very nice property to work with. And one way to make an arbitrary query preserve differential privacy is to first study how sensitive it is. So how much does the output depends on the input. And we can study that in fact, a very general setting. So if you have just a function between two metric spaces, you can always define this quantity, which is the maximum multiplicative impact of given two arbitrary inputs. So for differential functions, this is essentially an upper bound on the absolute value of the differential. So here are just two small examples. For a linear function or a fine function in general, this is going to be the multiplier component. And for, multiplication or the square function and so on, is going to be infinite, since there is no way to bound that arbitrary without taking a specific point into account. Okay, and once you know that, you know this quantity, you can make a query private by just adding enough noise, and the noise is going to be calibrated on the sensitivity. So if the function is very low sensitive, let's say it's a constant, you don't have to add any noise in order to make it private. It's already private. But if it's the identity function, then you're going to have. What Reed and Pierce did in 2010 is to notice that judgments which are very similar to those of linear, except from grades, real valued grades, can be interpreted as a sensitivity property. So you just take a typing judgment, you add real values to all variable type pairs, and it can be interpreted as to mean a sensitivity condition. So here are a few examples of sound judgments. The first one say that a linear function in 2 variables, it does a number of times each one is used, as in linear logic. For the square function, as I was saying earlier, it's infinite sensitive in X. And if you want a more complex example, because in the language you have recursive data types, you can deal with lists, for example, and sorting is actually 1 sensitive. And you can prove that in the system. Okay. As for the semantics, it is what you expect if you have some knowledge of the categorical semantics of linear logic, meaning you have category with all your products, co-products, and so on. And the main point is you have a compatible graded comonad. So this is the main thing that does the annotation, essentially, the real value annotations. And the category of metric spaces is one such category. So it is a model of fuzz and the intended model. Okay, it can be lifty to metric complete partial orders to deal with recursive types and so on, but I won't go into that. So here is for the state of the art. Our goal now was to go beyond this notion of global sensitivity and to design a corresponding type system. The main issue is that it is often infinite. I get the example of the square function, but it's also the case for a number of useful queries. And the reason intuitively is asking for uniform bound on this quantity is way too strong. And actually, in practice, we are only interested in the sensitivity at a very specific point, which is the real data set. So instead, we're going to study local sensitivity, which I'm going to define formally in a minute, but intuitively it's just a sensitivity, but at a given point. So instead of considering the Lipschitz constant, we're considering the derivative in a way. And it's interesting to study because it also can be used for differential privacy. It is slightly more complex. You have to use frameworks such as PTR. There are also other ways of doing it, but the only thing to know for today is that it is also useful in the context of privacy preservation. So the notion of local sensitivity we are studying is a bit more general than one found in the literature. We are considering sensitivity at point X, and here is our novelty, at radius K. For otherwise, we won't be able to compose the sensitivity, but the details don't matter that much. We're asking that for any point in a given radius, so for every x prime such that the distance with x is smaller than a given radius, then we have a bound on the output of the function. So we have a bound on the distance between f of x and f of x prime, just as before. So the reason we introduced this is to be both a reasonably low approximation of the local sensitivity used in the literature, that is with k equals 1, but still being composable. And just as an example, for the square function, you get 2xk, so k being the radius and x being the point, which is very similar to the derivative as we expect. Okay, so here is the type system we considered and we introduced. So the types are pretty much the same ones as fuzz, except that the annotations are very different. Before, the annotations were real values. Now they are functions, and not trivial functions. So I will spend some time explaining what's going on. You have two. So you're taking a value as first argument, then you're taking a number, which is a radius you're considering, and the output is going to be some sensitivity value. And we also require some syntactical properties to hold, such as monotonicity in the radius, this kind of stuff. So these are going to be our notations on arrows. And in here we say that these co-effects are dependent because the grades of coeffects you can attach to a type tau depends on, it's not the same for every single tau, basically. Whereas in fuzz, the coeffect for tau would be the same as the coeffect for sigma, would be, and not just real values. Okay, and now we can consider considering judgments as follows. So we have a pair of, a set of pairs of variables plus a coeffect, a global coeffect. Here, S, I mean a context-wise coeffect, rather. S, which is a function that takes all the values, all the radii, and gives you back a number. And the reason we do not add a coeffect to every single variable, as in fuzz, but instead in a context-wise manner, is just to have better bounds. But from a purely theoretical point of view, we could also do like in fuzz. It's just way more precise in this way. For example, we are able to type multiplication, which doesn't seem that impressive, perhaps, but it's infinite sensitive when we consider global sensitivity. So it's nice here to be able to give exact values. And I will give the typing judgments a bit later. Okay, so here are the rules. I mean, a subset of the rules. So, you know, to type a variable, you have to give 1 as a coeffect. Okay, it's a bit of a special one, but the idea is that you do not depend on the value x, and you just, if your inputs are at distance k or bounded by k, then your output is also bounded by k. So it really acts as our 1 here. A bit more interesting, because in order to abstract a variable, you have first to put the coeffect in the correct form. That is as a sum of two coeffects, one of them associated with gamma, and there was one associated with sigma, meaning you first have to apply weakening. And this can be very costly. As during introduction, you may introduce infinite sensitivities, but this is what it is. And for elimination, so here is our elimination, but more generally for all the elimination rules, you have to consider some kind of scaling, as in fuzz. But here the scaling depends on the term you're considering. So it's kind of, I used a scaling notation, but it's more like function composition under the hood, but should be interpreted as scaling. Anyways, and we have also introduced other operations and coeffect to deal with, for example, disjoint sum and so on. And one nice feature and a reason to subsume fuzz, meaning that if we only deal with specific functions that mimic the behavior of fuzz, meaning just linear combinations of the radius of the radii and not dependent on the point we're considering, this perfectly encodes fuzz. On all our typing rules, just become fuzz as well. So we completely subsume fuzz here. Okay, and as I was saying a bit earlier, we can also add typing rules for all kind of primitive operations, so operation on list and so on. But the one I want to show is just multiplication. It can look a bit scary at first, but you can notice that it is just saying that it is the first term times the difference in the other one, plus the second terms as the distance in the first one, plus the multiplication of the two distances. So it's very what you would expect, and it's quite intuitive after some time. And we can derive the exact sensitivity of the square function, to take our example again. Okay, so let's talk a bit about the semantics. It is almost, the base is the same as in graded linear logic, meaning you have monoidal class categories with your reckoning, coproducts, and so on. And the novelty is to consider a graded, a dependently graded comonad. So this was introduced recently in 2024 in a quite different setting. And to the best of our knowledge, this is the first work considering it from the point of view of a type system. And we think it can be useful in a variety of contexts, but here at least is in the case of local sensitivity. And given this semantic interpretation, one of the main results, semantic results, is that if you can type a term E with some annotation S, what you obtain is a bound on the sensitivity, on the local sensitivity of E, one already known in the literature and so on. And the conclusion you should keep in mind is that if you are able to type a query, then you know how to make it differentially private. Okay, just to be somewhat concrete, I will give a few case studies. So first of all, I will go back to global sensitivity because being able to derive a local sensitivity as intermediate steps can be useful, and afterwards I will talk a bit about something more specific. So, first of all, global sensitivity analysis. If you consider judgments which do not depend on the value, so here is such judgments. They can have a variety of forms, but this is the one that encode first, for example. You can consider other ones. What you get, in fact, is a bound that does not depend on the point you consider, so it is a bound on the global sensitivity. And what we showed with specific examples is that it's not uncommon for the bounds on global sensitivity to be better than the one we obtain in FUS. So being able to first talk about local sensitivity, talk about some compensation stuff allows you to at the end use standard techniques such as the Laplace mechanism, but with less noise, which means more accuracy for the same privacy guarantee. Okay, and the second example I want to talk about, which is perhaps more specific to local sensitivity, is some simple algorithm I want to show you how to type. So let's consider that we have just a bunch of numbers, let's say normally distributive numbers, and we want to find an interval containing 95% of the values. So a way of doing it, there are many ways, but this one has the advantage of using only a single primitive, is first to compute the mean, which is equal to the median, and then to compute the standard deviation by using some multiplicative factor of the difference between the quartiles. Doesn't really matter, this is just a way of doing it, that's using just quartiles. And at the end, you return the two numbers you're interested in. So the only primitive we need, as I was saying, is a quartile. It is already well known that you can give this formula for the local sensitivity of the quartile, and consequently you can add a corresponding typing rule in the system. So here it is. And using this rule, what you can derive is that function I have just written, typical range, is taking a set of integers, giving back a pair of integers, but with some special annotation S, which is a function from the point in the radius to a quantity, which if you take a closer look at it, closely resembles the structure of the programs, as you would expect. But there is 2 times the local sensitivity of the second quartile, because we're using that twice, one in each coordinate of the result, for example. So it's very close to the structure of the program. But what is most important to notice is that it is finite. Whereas in FUS, the best we could write for even the quartile would be infinite. And now what we can do is apply any framework we want that takes a query and a local sensitivity bound as input and give you back a new query that behaves almost exactly the same, apart from generating some noise, adding some noise to it, and you get back a privacy protecting version of it. Okay, so let me conclude with first a summary of what we did. So what we have designed is a type system for deriving some upper bounds on the local sensitivity of functional programs, and I've shown how it can be applied to differential privacy. And about future work, one of the main points to notice is that our calculus is quite non-specific in its syntax. What I mean is that I expect that apart from the definition of the semantic definition of the operators and so on, maybe the specific grades we use, because it was function from a value to a number with some syntactic restriction, but using a different grade, I think we can apply this methodology of dependent coeffects to a wide variety of problems, including maybe time complexity and information flow control. So if you have some ideas about that, I would be more than happy to discuss. And another direction is to study type checking, because the constraints we would be considering while writing type checking algorithms are quite difficult, because we're dealing with functions all the way. So, we use only a subset of all possible functions and so on. But since we're reckoning, I think it is quite a difficult problem. And once again, I will be more than happy to discuss that. So feel free to ask if you have any question.
Okay, we have time for a few questions. Yes.
Yeah, thank you for the talk. So, because it's still on the slide, so other dependently graded comonads, do you have some at hand, some in mind?
So yeah, are there also examples of dependently graded comonads?
Yeah, so what comonads do you have in mind there? Because
okay,
you mentioned cost specifically, but
so what we're requiring is essentially the grade to be able to depend on the object. So we have a different grade for each possible object.
Sorry, do you have examples of those? More examples that you're excited about?
Yeah, there are more examples in the paper. They introduce the notion, but I don't have like easy, specific computer science relevant example at the end. So.
Okay.
Yeah.
Okay, we have time for another quick question. So I'll ask real fast. Can you tell me a little bit more about what would be involved with decidable type checking? Like you mentioned the complexity of the constraints. How practical do you think it would be?
I think the main issue is the line you draw with weakening. So we have a weakening world and that depends on inequality relation between coeffects. And depending on how loose or how strong it is, it can become very subtle. Like even for subject reduction, we have to be very careful about the hypothesis of our inequality relation. And I believe, for example, that if you take arbitrary, just semantically valid weakening, then it becomes quite clearly undecidable, I think.
Okay, thanks. Sounds challenging.
Thank you.
Okay, thank you very much. Okay, so for the second talk of our session, we have Hema Gomi, who is from CMU, who's going to be talking about some dependency tracking using substructural logic. And I want to say that this is also one of the distinguished papers of POPL'.
All right, let's talk about substructural dependency tracking. First, okay, so what is dependency tracking? Basically, if I'm holding a computation in my hand, I want to know how its outputs are affected by its inputs. And this is super useful in a domain like security, where if my computation is processing, say, passwords or cryptographic secrets, I want to make sure that it's not leaking information about those to, say, the internet. But the sorts of data provenance and separation properties that emerge out of dependency tracking are also super useful for things like, say, concurrent and distributed systems, and program slicing, and build systems, and reactive programming, and so much more. But in all these cases, there's certain extra questions that sometimes arise that lie just beyond the reach of standard dependency tracking techniques. Things like, how often do I depend on this piece of data? And if I am said to depend on this piece of data, is that dependency guaranteed? And finally, in what order am I inducing these dependencies? And our work is an attempt to answer all these questions in a unifying and satisfying way. And so, like, understanding all this dependency tracking stuff is really why we're doing this work, but I think it's a lot easier to understand how we did this work, starting from the substructural part of the title. So let's do that. And in particular, the place I want to start is affine types in Rust. So if I'm in Rust, and I've got this capital S string bound to this variable x, and I pass x to func1, and then I pass x again to func2, Rust will give me a type error. Rust will say, well, you already consumed x once when you moved it into func1. You can't consume it again when you want to call it on func2. And this is because data in Rust is ephemeral. You can only use it a single time. And it's exactly this idea of ephemerality, or change over time, in this case, variables being deleted, that leads to resource reasoning. And we can generalize from this picture of singly bounded consumption to finitely bounded consumption using something called bounded affine types. And a simple syntax for this might look something like this, where if I have I have this function f whose signature goes from nat with 3 fuel emojis annotated to a nat. And the semantics of the fuel emoji is that each one indicates one allowed usage of the variable, or of the input variable. So I'm allowed to use x twice or thrice, but I'm not allowed to use x 4 times, because by the time I get to the 4th usage, the type checker says, okay, you've run out of fuel for x, so you can't use it anymore. So no dice. And the thing to observe here is that the number of fuel emojis on the input dictates the structure of the body of f. And so to get from this picture to ours, all you need to do is sort of flip the picture around a bit. So instead of using restrictions on the input to create resources, you want to use restrictions on the output to create resources. And that might look something like this, where I have this function g that goes from a coin nat to 3 coin nat. And the meaning of the coin nat on the input is that whenever you use the input, x, it induces a single coin worth of resources. And the meaning of the coins on the output is that any valid body of g can't use more than 3 coins worth of resources. But I've actually lied to you slightly here, because when you move from the input picture to the output picture, what you start caring about is not usage of variables, as in the input case, but the running of computations. And this is a really, really important and deep theoretical choice that is actually forced and not a design choice at all. And so the way to begin to understand this is, okay, you can think of the coin nat type as a thunk, or a suspended computation. And you can think of all these exclamation mark operators as forcing the thunk, or running the contained computation. So what matters for inducing a coin is not mentioning the variable x, but running the computation it contains. In particular, something you can do that's totally valid is binding y to the result of running x, inducing a single coin, and then using y any number of times you like, because y is just a type nat and doesn't induce any coins. It's just a value. And so to understand like why we're focusing on this running of computations versus mentioning of variables, which might seem like kind of an arbitrary design choice, you might think of the semantics of the fuel emoji as being consumed by the body of f, whereas the semantics of the coin emoji is to get produced by the body of g. And so this idea of like consumption versus production sort of really nicely characterizes co-effects versus effects, where co-effects are all about like consuming variables by using them, and effects are all about producing things by virtue of running computations. And there's a stronger proof theoretic justification for this in our paper if you're not satisfied with this explanation, but for now I want to move on to some examples. So the first example will return us to dependency tracking land, and in particular we want to track very coarsely, not as powerfully as the last talk, but very coarsely some measure of the amount of information regarding some password that we depend on. So this password checker module is going to export some affine resource lock, where affine just means the quantity matters. And it's going to export this method check that takes a password as a string and returns me a Boolean that says whether I got the password attempt right or wrong. That's also annotated with this lock. And so when we go to use check, if we use it just once, we induce a single lock in the type. If we use it twice, we induce 2 locks in the type. And if we use it twice but only annotate 1 lock in the type, then we get a type error because the type checker knows, well, you've produced at least 2 locks worth of information about the password, so this is no good. So like go away and do something else. So you can't do that. But interestingly, something you can do is in the first line here, you can choose to annotate the type with 2 locks instead of just 1 lock. And the reason for this is due to a principle called strictness, which specifically says, or rather lack of strictness, which specifically says, given a dependency or given a dependency set, or a resource context rather, you can tack on another resource onto it, here a diamond, basically for free without doing anything. And so you might wonder what reasoning abilities we get out of removing this ability to give ourselves more resources for free. And it turns out it lets you reason about authorization in a nice way. So this authorize module starts by declaring this strict resource diamond. And it also declares this method authenticate, which takes in, again, a password attempt as a string and returns me, if I get the password wrong, it gives me a unit with nothing on it. And if I get the password right, it gives me a unit with a diamond on it. So the idea of this authorize module is that the only way for me to get a hold of a diamond is to witness a successful authorization. That's the only way for me to do it, because again, I cannot give myself a diamond for free, and there's no other way to get a diamond except by calling authorize. And so if you have some sensitive computation that you want to guard in your program behind authorization, all you have to do is mention a diamond in one of its arguments, and then anything that hasn't witnessed a successful authorization and therefore doesn't have a hold of one of these diamond tokens to give to it cannot call that computation. So just to flesh out the example a bit here, you can call authenticate with the password attempt string. And if you get the left injection, then you got the password wrong, and you got to maybe run some cleanup logic or error handling or something else. But if you got the password right, then that's the exciting case. And you have this token that's a unit with a diamond on it. And to call the secured function, you can pass it an integer with the diamond from the token stapled onto it, and then pass that whole package into the secured function, which will type check because it witnesses your successful authorization, and that's very good. And our final example is going to be protocols or seccomp. So I'll go through this slowly. And so there's this pattern in a lot of really high security or sensitive software like web browsers or web servers where they start out needing a lot of permissions because they say need to create lots of temporary files or spin up network sockets or take locks on a bunch of resources and so on and so forth. But once they've reached their running state, they really don't need all those permissions anymore. And so what, like, say, Chromium does is it tells the operating system, OK, from this point forward, I'm not going to need most of my permissions anymore. And so I'm only going to use some little carved out piece of your API surface that's like safe for me to use. And if I violate this contract with you, kill me, like terminate my process immediately because I've been compromised. And so we can encode this really widespread pattern, as it turns out, in a lot of secure software in our system by working with what are called immobile resources. So we declare these two immobile resources drop and high, and what an immobile resource is when you mention it in a resource context, all it means is roughly it can't move around. There's a slight extra technicality here that I'm not mentioning that you can look to the paper for full details on, but just continuing, we go on to declare a structural resource low, which just means it's not restricted at all. So low is just, it can appear anywhere, it can be weakened, or it can be added into your resource context for free. There's no restrictions on it. And then we declare these three operations, drop, high, and low, that each induce one of these resources. And so a valid pattern of usage is to run the high operation, and then run the low operation, and then drop privileges, and then do a low operation. That's totally fine according to this protocol. And another valid pattern of usage is to never call drop at all. So you can do low, high, and that's totally OK, because you just never call drop. But what's not OK is for you to do a high operation, and then drop privileges, and then a low operation, and then do another high operation right at the very end. Because now you've dropped privileges, which means you've got this contract with the operating system, and then you're still trying to do a high operation after it, which is no good, right? So that's a type error, and the program rejects it, and the type checker rejects it because it mismatches the declared protocol in the type. And so the thing to take away from all these examples is that the production perspective characterizes naturally a very different range of resources than the consumption one. And so, like with this quantity-sensitive leakage example, it's very natural to think of a computational process as like producing or generating some information that you then need to keep track of and control in like a quantity-sensitive way, rather than thinking about it as some sort of matter of subsumption, I think. And especially with capabilities, like the structure of a capability is that it's a token produced by some authorization or validation computation that you can then present to other things that need authorization or validation, and not, it's sort of confusing to think about how you'd model it as a matter of consumption. And the picture is slightly less clear for the seccomp example, because of course you could encode that using some sort of like object-oriented linear type state, right? That's a very classic maybe use case of it. But it's interesting to think about the ergonomics of like passing around the entire operating system kernel as like a type state object and trying to work with the protocol that way, versus just selecting out the operations you're interested in and sort of declaring an ad hoc protocol on some ambient operations that you want to control right at that local context, as we did. So there's a sort of an argument for the production perspective there as well. And there's more examples in the paper. And it turns out we get a 3-for-1 deal on capability, quantity, and protocol safety. And to explain how we do that, I have to pull back the curtains a bit and explain. So when I showed you this thing about, when you have a resource context in your hand, you can tack on, say, a diamond onto it for free. I was really applying this principle called weakening from substructural logics. So we were weakening a diamond into our resource contexts. And when we removed that ability, we were removing weakening from this diamond resource. But really what was going on under the hood is that there's this subsumption relation defined on resource context that lets you go from a resource context without a diamond to a resource context with a diamond. And when we made diamond strict, we made it so that that case of the subsumption relation was dropped away from diamond and could no longer be used to obtain a diamond for free. So diamond was a strict resource. And likewise for contraction, when we made locks sensitive to quantity, we removed this rule of contraction that says, you can collapse 2 locks into a single lock. And so we made lock into an affine resource. So we removed that case of subsumption again. And the situation is very similar for exchange. Like when we removed this sort of pseudo commutativity property of high and drop, we again removed the case of subsumption that lets you commute these resources. And then we ended up with immobile resources high and drop because we removed that case of subsumption. And so you can mix and match all these modes according to this mode lattice in our system, and actually this is only part of the mode lattice. But really the takeaway here is there's this subsumption relation on resource contexts that fully sort of captures the substructural properties of our system and everything we're interested in that respect. And with that subsumption relation in our back pocket, we can state soundness now. So you can read this as, if we've got a well-typed resource, or sorry, if we've got a well-typed program under some resources A1, A2, and forcing that program evaluates it down to a value, and produces some resources B1, B2, then the resources B1, B2 that were dynamically produced are substructurally compatible with the resources statically specified in the type of the program. And to see why this is so powerful and significant, I think it's really easiest to apply it to each of our safety properties. So Linden in 1976 defined a capability as a token used as an identifier for an object such that possession of the token confers access rights for the object. Okay, so really you can think of the core safety property of capabilities as this idea of unforgeability, because you need to not be able to obtain a capability or this kind of token in a dishonest way. And just as an aside, he interestingly continues to describe the sort of resource semantics of a capability, because he explicitly says it's actually okay for you to reproduce capabilities. So he's kind of saying here that contraction is okay for capabilities because the quantity doesn't matter, which is interesting. So even back in 1976, they were thinking about capabilities secretly as resources. Okay, but that aside, we can think of the soundness of the capability safety theorem as, if I have a well-typed program whose resource context contains a diamond, and that diamond is strict, then that program gets pushed down to a value, and when it does so, it produces some resources that themselves contain a diamond. So what this is saying is that when I have a strict resource statically specified in my program's type, its computation really honestly has to witness it. It really has to run a computation that honestly gives it that capability. And so the sketch of the proof for this goes something like, by soundness, we know that the dynamically produced resource context is substructurally compatible with the statically specified resource context. And by strictness, we know that we can never get from a resource context that does not include a diamond to a resource context that does include a diamond. So if you combine these two, you see that if the B1, B2 resource context on the left inequality did not already contain a diamond, there's no way we could conclude this equality because we have no other way of obtaining a diamond besides already having one on the left. Okay, and quantity safety proceeds super similarly. So if we have a well-typed program with some resources A1 and A2, where that resource context contains n locks, and lock is affine, that program gets pushed down to a value and dynamically produces some resources B1 and B2 containing k locks where k is upper bounded by n. And the proof sketch for this goes really similarly to the last case. Again, by soundness, you have that the dynamically produced resource context is substructurally compatible with the statically specified resource context. And by affinity, you have that that two locks on the left side of this inequality cannot be collapsed into a single lock on the right side of the inequality. So if you think about what would happen if the B1, B2 resource context had more locks in it than the A1, A2 resource context, it would be totally impossible to conclude this substructural compatibility that's required by soundness. So you know that the number of locks in the A1, A2 context must be an upper bound of the number of locks in the B1, B2 context. And of course, if you switch to if you drop strictness and go to the linear case, then this bound becomes exact. So k has to equal n because once you add strictness, you know that not only are you upper bounded as far as the number of locks you can produce dynamically, but for every single lock that appears in the A1, A2 resource context, you really honestly have to produce it in the B1, B2 resource context because you can't obtain any more by weakening. You cannot use weakening to resolve the inequality between k and n, so k has to be exactly equal to n. And protocol safety, well, there's a lot of different facets to this, so I'll state like a fragment of it. Basically, if you have a well-typed program with some ordered resources A1, A2, ordered meaning they lack all structural rules, all bets are off, they're not doing anything interesting. And you push that program down to a value, then it produces some dynamic resources, namely some dynamic resources where A1 must appear before A2 in the resource context, so it's a relative ordering. And one satisfying resource context for this on the dynamic side is one where just A1 and A2 in the most boring way appear right at the front of the resource context. So you have A1, A2, and then B3, where B3 is some dynamic resource. And the proof sketch for this is totally analogous from soundness, weakening, contraction, exchange, just as in the previous two cases. Okay, so there's a lot more in the paper. There's, curiously, 2 more structural rules I haven't mentioned here, which is interesting because most people think there's only 3. It turns out that you can think of the entire language I've presented to you as a constructive Kripke semantics for substructural logics, reified into a programming language by analyzing its computational properties. There's a really interesting connection between the quantification connectives in our core calculus and in our language that I haven't presented here, and this idea of shifting in linear, nonlinear, and adjoint logic. And we had to deploy this very cool new proof technique for capturing logical relations for open-ended effects because of all the quantification flying around in our language. So do check that out. And there's, of course, many more examples in the paper. But really the takeaway is that the effectful view on substructurality shown here like unifies a totally new set of tools, or sorry, an old set of tools, but a really useful set of tools newly under this umbrella where previously they were not thought to be connected at all. So that's it.
Okay, we have some time for questions.
Hey, thanks very much. This is really beautiful work. I noticed that all of your soundness theorems had a clause that said, if it's well typed, then it does produce a value and these resources.
Yeah.
So can you handle non-termination at all?
The logical relation as stated is only for terminating programs. I have worked through a step index relation on my end that I'll put out later, maybe in another paper. There's no issue with non-termination, but besides you have to talk about safety up to some idea of non-termination, right? But that's a standard thing. Yeah.
Thanks very much.
Yeah.
Yeah, thank you for the talk. You mentioned early on that your capabilities are directly tied to computations, which makes sense, but then it looks like the language that you're presenting is lazy, and normally the approach for strict languages is to put capabilities on arrow types, which are of course the only value that can sort of encode computation. So is there a fundamental reason why you can't do this, or is it just a different approach?
Yeah, so you can think of the resource type. Maybe it's easier for me to have a thing to gesture at here. Oh. So you can think of these resource types, well, this is fine. You can think of these resource types as a suspension type in the sense of maybe call by push value or something. So this is in a polarized sense, this is U of f, or in a non-polarized sense, this is a strong monad. So basically, we just have a custom little type connective that does the suspension for us, rather than sort of overloading the function connective, which most people use as a suspension connective with extra information. So we just punted that off into another type.
Okay, but it's not you don't think that it's more expressive, it's just a different expression.
No, it's just a different, yeah.
Yeah, okay, thank you.
One more question?
I'm really happy you mentioned adjoint logic, and I wanted to know if you can if you don't mind giving like a little. Oh, okay. I thought the microphone was speaking to me. If you can give like a little taste of like how the adjoint logic formulation might like make things a little differently. Like, do things get more expressive or more complicated?
Yeah. So the really interesting thing about this is actually, as of yesterday, there's an adjoint logic formulation of this that my advisor works on with a different student, and so they proved that it's like formulated as this like sequent calculus sort of thing, and they proved that the type system they have there is decidable, and the way this work and that work interacts are such that you can carry over the decidability proof like totally mechanically to our system. So like indeed everything I've shown you here is decidable. You can kind of think of a lot of this as like a Kripke interpretation of a lot of adjoint logic in a certain sense that I have yet to make like super fully formal. But yeah, it's really interesting follow-on work, and I'd be interested to talk to you about it in more detail. Yeah.
Sounds good.
Last question here.
Thank you for the great talk. I think at some point you showed the cuboid and you called it, or a cube, and you called it a mode lattice. And I was wondering if this was an intentional choice of words. Maybe I'm missing something and it's obvious, but is this connected to model type systems or soft model logic?
Yeah, it's super connected to modal type systems. It's not an accident that I said that.
Could you elaborate on like the connection?
Yeah, we can take this offline, but the one sentence summary is you can think of this as basically some kind of adjoint logic, which itself is a modal logic, or like a semantics for an adjoint logic.
Cool, thanks.
Okay, let's thank him again. And I'll remind you, next we have the PC report and business meeting over in immediately.